Good morning, Reddy sir.
Hello, sir. Sir, good morning, sir. Vanakkam. Good morning to all.
Yeah.
Thank you.
How are you, sir?
Yeah, I'm fine, fine. Thank you. Thank you, sir. Thank you.
Okay. I think it is around 11:30 night there.
Yeah. Exactly 11 o'clock.
Okay.
Yeah. Now 1 hour difference. Just okay.
Okay. We'll wait for a few more minutes.
Yeah.
Let's
No,
see.
no, no problem. No problem. No problem. We can wait.
Yeah. 1 minute we'll wait and then we'll start exactly at 9:30, sir.
Okay, sir. No problem.
Professor Goda, are you there?
Yeah.
Yeah. Can you start, Professor Goda? Bere Goda?
Hello, sir. Amit Kumar here.
Yeah.
Yes,
Amit
sir.
Kumar. Will you start the program?
Yes, sir. Sure, sir.
Yeah. I will just introduce and you can take over. Okay. Good morning to one and all. Today we have Dr. Reddy with us, who has come all the way from Canada to deliver the talk. So my colleague, Professor Arun Kumar, will introduce Dr. Reddy to you. And once the introduction is over, Reddy sir, you can take over the session, sir.
Okay.
And
Thank you.
I
Thank
wish you all the energy day today. Today is a World Energy Day, and we thought that Mr. Reddy would be a right person to deliver the first talk because he is working in that area of renewable energy, and he has done a lot of research work in the field of cathode, anode, electrolytes, and lithium-ion batteries. So we thought he will be the right person to start on this day. So I wish you all World Energy Day and try to conserve our nature by saving fuel and try to use as much as renewable energy in your daily life. With this, I request my dear colleague, Professor Amit Kumar, to introduce Dr. Reddy to the meter, and later on we can start the session. Thank you, sir. Reddy, sir.
Okay. Thank you very much, sir. Thank you for your kind words. Thank you, sir. Thank you.
Dr. Amit Kumar, over to you.
Sir. Dr. M. Reddy obtained his PhD in 2003 in the area of material science and engineering, and from the Bordeaux University, France. And he worked at the Department of Material Science and Engineering, Chemistry and Physics, and also the and also National University of Singapore in June 2019 to August 2021. And also he's worked at the Center of Excellence in Transportation, Electrification, and Energy Storage. And from Hydrocubic, so Canada. Currently, he is working as a senior professional researcher at New Graphite World. So that is in Canada. And his past 21 years, he has conducted the leading research on materials for engineering storage, for energy storage, so material processing and characterization, and also the development of in-situ techniques for this renewable technologies. And also already published more than 210 papers in the various international journals, and also obtained an H index of 66 with over 16,450 citations. And also and, uh, and also and also he is placed within the top 2% highly cited researchers in energy. So uh, out of 1 lakh 86,500 researchers in 2020. And also he's serving as an editorial advisor, board member in actually various journals. So it may be in elsewhere, or it may be in actually so Scopus journals. And also he is awarded with outstanding science mentorship award in 2010 to 2018, and also inspiring research mentor award from 2011 to 2019. And also 2021, and also in the battery materials, so this electrochemistry award from this Electrochemical Society of India, and also from Indian Institute of Science, Bangalore. Okay, sir. With this, so it is a brief introduction about Dr. Reddy, sir. So it is over to you, sir.
Okay, once again, thank you very much, sir. Okay, just I would like to know my slide is visible and
Visible,
voice.
sir. Visible, sir.
But the slide is
This
moving,
audio and
sir.
video is visible, sir.
Okay, okay. I think slide is we are able to move the slide.
Yes, sir. It is.
Okay. So once again, thank you, Chairman, for especially Professor Raju for organizing the excellent workshop. In fact, yesterday I've seen that the inauguration meeting. It was really excellent meeting, and then with the speakers. So today we are going to discuss, and I'm going to discuss on the especially nanomaterials, or what we call as the mechanical engineering, some composite materials for energy storage. Especially, I think all people are familiar with what are the electric vehicles or your mobile phones, and what are the importance of like materials for batteries, or what are lithium battery, etc. Okay. So also I'd like to make it this talk should be more simpler, so that since the background is from mechanical engineering, also from the different background, some people from science also. So I would like to make it a little bit simpler, so that all people can follow the some simple terms, so that at the end we are able to know that what are the importance of materials, or what are the color energy storage, and how mechanical engineers we can contribute in terms of not only in material design or material processing. And another way is that especially when we wants to make a battery pack, how we can contribute, or you want to integrate the battery pack into your like engine, how we can contribute like that. So that I'm going to slightly link some slides to how all the engineering different branches we can work together in this particular area. So since the conference organizer, they've given me almost like 1 hour 30 minutes, maybe I have to finish by maybe 10 minutes. I'll try to give the time for the question and answer, so that so also already 5 minutes we finished due to introduction everything. So without any further delay, just I'm going to start this talk saying that again thank you for the especially Ambedkar Institute of Technology, and also all the management, and also AICTE for this constant support, and then for the organizing the excellent workshop. So as you can see clearly the importance of these workshops. In fact, thanks to Professor Raju, in fact invited with various eminent speaker with a different background. I think people are covering with the different aspects of the what they call a material or materials for composite materials, with a different type of application starting from different areas. As you can see that, for example, a first talk is given by shape memory alloys. Again, the importance of alloys, if you take it in terms of the, for example, in a battery casing, although I can claim the battery is very important. If you talk with alloy people, I think if you make a real battery casing, we need lightweight casing. So that's why importance of alloys is very important. Again, similarly, I think some other speaker also talking covered by the different area of the electrical material science and what I call composite materials with the different type of the applications. So presently, I based in Canada, where the Quebec, both the English and French-speaking state, is the only place. And also, in addition to other beautiful seasons, especially maybe I think this again the climate change this year slightly differences in the climate also we can see, especially January, February we can see the this type of heavy snow somewhere, and also sometimes may go to extreme low temperature also. So this is my outline of a presentation, so that I'm going to introduce the things and especially importance of research. I think anybody can do. That's why I'm going to tell that how the like introduction and also material processing, and then especially today is a sustainable I think energy, what the energy be energy day. So that's why we are talking about the what are the real materials and sustainability, and what are the challenges etc. in this particular area. So again, I'm telling these are small examples. I think last 15 years I was in 17 years in Singapore, where we trained a lot of science and engineering students for the in the area of energy storage. I think starting from junior college and high school, and then some students are able to go in later. They go to into mechanical engineering, or some people are going to chemical engineering, or some electrical engineering, etc., etc. They're doing the higher studies, and few people are also doing that in the energy some research also. So these are the small contributions. We've been some publications we published in the various national and international journals, especially some few examples. It clearly indicate that with the proper facilities, I think everybody can do research. This is almost like 1 year part-time research with I think few groups of the few good projects we publish. And also, some interestingly, the students are able to present in the various national conferences held in science and engineering fairs. Some people are able to present in the international conference held in the USA and especially Japan, and then other part of the world. So there are small group from Singapore as well as many people from India. I think nearly 6 to 7 giant students have been trained the PhD in the area of energy, like lithium battery and energy storage material in our laboratory. So these are small collaboration within Singapore as well as India and few other part of the world. So also my research interests are, so I work for some mainly focusing on the new materials for cathode anode. So when then some other areas also due to time limitations, I'm going to touch up what are the, since lithium batteries are very popular. So I'm going to discuss about the what are the principle and what are the challenges in these particular areas. And also if time permits and some other examples, sustainability at the end. And due to time limitation, I'm not touching in the other areas of the our interest. So again, I think all people are familiar that our human history prosperity started in the early Stone Age, Copper Age, Iron Age, Rubber Age. You can see the Silicon Age made them think in a different way because of the discovery of vacuum tubes, computer, plus especially our phones, etc. Again, the importance of composite material again at the year 1980s. I think there is a lot of interest has been happened because people are thinking about the always thinking about lightweight materials and then our good mechanical properties, etc. That's why there is the importance of this conference, or like especially mechanical engineers play an important role. Especially year 2000, there is a lot of interest in the functional what they call a nanotechnology. There is huge interest in the materials during year 2000. Now people are calling the molecular age. Future always people are talking about the intelligent low carbon age material, in the sense that always people are thinking of how to reduce the pollution, especially that will we know that the pollution is affecting our especially healthy lifestyle, etc. That's why always people are looking for especially how to reduce the pollution in a different way, in a different aspect of the, especially in terms of materials. So now again, I think in general, in terms of the heart, always anyway, again the people are talking about the heart areas. Again depends on the, and we know that presently we have the problem with related to energy, environment, and healthcare, and also especially water technology, etc. Again, our job is to maintain sustainable environment and a healthy lifestyle. And in addition to this one, especially idea that we always have to reduce the air pollution, especially if you talk about the people are talking about a smart city development. For that case, we need a good infrastructure as well as a And also, anyway, in addition to this one, there are a lot of other factors, example, waste management, etc. also, or city planning, etc. also take into consideration. Now, in terms of materials, we broadly classified in based on the building materials, again, electronic material, energetic materials, especially engineering material. I think these are very important, iron and steel. Again, for example, superalloys, I think again, these are all the talks we covered with a few previous speakers. And also, based on the physical properties, we broadly classified metals, semiconductor, insulators, magnetic properties. I think some talks also covered by this kind of a workshop. And optical material, again, if you're talking about the, for example, electrochromics, or for example, photonic applications, or metamaterials, these are all the things, these are all the optics. And dielectric and radioactive thermoelectric materials, also some talk is given by this in the workshop. I'm going to focus on especially energy storage materials, mainly focusing the material the electric vehicles, or you talk about the smart grid, etc. So now I think to solve the present environmental problems, we need always green energy, green renewable energy technology. Again, this technology depends on what type of sources. For example, here there is a lot of water. That's why hydroelectricity is very famous. Again, place like India, we have a lot of use and use some solar energy. And again, other type of, and again, the batteries are almost like universal. So if you talk about the any major cities, including that, always people are talking about, means 50% of the pollution in the major cities is coming from the four wheelers like cars. That's why use of the gasoline vehicles. So again, so there is a lot of interest, is common interest irrespective of any country or any region. That's why always people are looking about the producing material their own like a region or fabrication of it. That's why at the end they can reduce the cost, and then they don't depend on the any other country. That's the way people are thinking about the producing the materials, their own battery packs or their own what they call minerals, etc. In general, what they call energy storage or renewable energy technology is interdisciplinary area, especially we need in terms of science and also mechanical engineering, chemical and materials, electronic and automobile engineering. And again, I'm telling that in terms of the, as a material researchers, always you to think about the novel materials, especially people are looking about the how to improve the energy density or power density of this particular energy, because mainly the cost of the battery is high. That's why or the weight, when one way to reduce is to improve the energy density of this particular materials. Now I'm going to introduce the what are the importance. I think already we mentioned that importance of energy storage. Suppose you would like to, for example, batteries you would like to use for your own electric vehicles, or you would like to store, for example, solar or wind energy, or for example, you want to be a smart building. Again, the batteries will play an important role. I think this is the world data. Again, this if you compare them, the fuel price keep on rising up. So again, the idea is that in addition to the price, another aspect is always people are thinking about the environmental issues. Means we only we ways to we can reduce the CO2 emission by using the. I think we can reduce, for example, gasoline vehicles by use of the battery operated cars, etc. Now, people may ask what are the real challenges. Again, if you see that, for example, I think we don't have any problem with the portable because there we need lower energy. If you talk about EVs and plug-in electric vehicles or smart grid, again we need energy in terms of kilowatt and megawatt range. So here main issue is that, for example, the material should be low cost and safety, and also you need to be more efficient and long. There's a major issue, and cost is a major one. Safety, these are all important points you have to think to. So that's why there is a lot of interest in the, especially in terms of industry or research is going on this particular areas. So again, I'm telling this one example. So not only India, like we are throughout the many places, always people, the pollution is a major concern. That's why they're looking for the alternative energy storage devices. Another area also people are talking about in terms of the solar. I think if you want to select solar energy, again, sometimes in the battery, if you use the battery pack, again, the cost of the battery pack is high, and automatically this technology is the price of the technology is going to rising up. So that's why there is a interest for especially in the battery, like how to reduce the cost of the batteries also play an important role if you think about the solar PV technology. Another, I think all people are familiar about autonomous electric vehicle, the future. So what they call a self-driving vehicle uses artificial intelligence, and also it uses lidar and radar type of sensing technology. I think major benefits is that these are, we can reduce the lowering of fuel consumption as well as the development of the, also we can reduce the CO2 emissions, and also we can reduce the traffic congestion, etc. I think these are all very important. If you talk about smart city, I think we need a smart vehicles. So again, autonomous vehicles are the one way. Again, these are the revenue, and also at the end, also we can reduce the vehicular crashes, etc. Why? Because everything is managed by software, and then that's why it is very important. So this particular things. It clearly shows that if any autonomous vehicles, it is a little bit sensor, and then there is a GPS, and then it's a computer, and again their battery, and then your engine, etc. There, what I'm telling that there is a lot of opportunities for the especially batteries, material engineers, or scientists, or mechanical engineers, or civil engineering. At the end, you want to be electrical engineering, for example, sensor development, or computer engineers. All together, we have to work is very important. That's why there is a lot of opportunities. You see that I think the different type of companies are spending in this particular areas. Again, I think all people are familiar about the Tesla, and few other things are dominating this particular domain of this, especially this particular area. So now I'm going to introduce the briefly. I think all people are using, we are using this type of mobile phones. Once you open that particular opens or some problem, you may see somewhere. So depending on the battery pack or whatever it may be, you may see some small, this type of the pouch. So this is called like the pouch cell. Like you may contain negative and positive electrodes. I'm going to explain what are the components inside very clearly in the coming slides. So this is one example, particular device. Suppose the left feet, I think all people are using mobile laptops. It may use something like cylindrical cells. Same thing like 18650, so like 18 diameter and 650, like 65 length of the particular things, and depending on your energy or whatever the requirement accordingly, they can put so different type of the like for especially your laptop, etc. Again, for example, you want to be more energy. Again, always remember you to double or triple or maybe it's more number of cells you have to put it if you want like to run this particular battery into your electric vehicles. Again, so they use this type of cylindrical cells, put it in this type of packs again. So these are typical electrical vehicular battery pack. Again, remember, so not only one single cell, because you need something like, for example, if you want to use a bigger cylindrical cells are depending on your energy or whatever the requirement voltage. So you have to put like, that's why nearly around 7,000 cells that put it in the this type of particular battery pack you would like to run the car. So now you may ask you what are the opportunities for mechanical engineers, or for example, if you want to talk about, I think people are talking about the phase change materials or the cooling, sometimes in terms of what they call as the thermofluids, or suppose, for example, here we know that batteries little bit during the charge discharge, heat will develop. We want to cool the system, and again there is a lot of opportunities for especially mechanical engineering or electrical engineers to work, especially in terms of sensor development, etc. We can work together. So overall summary is that if you look for this type of big packs, we need a not a small laboratory. We have to work with the big industries, and then again the all the production, the cost, especially want to fabricate it, we need a big like millions of dollars they have to spend together again. So that's why, so usually in the university or any engineering lab or anything you can do, so or any R&D in any type they will do this coin cell. Once is so fine, they are able to do it either different type of design is possible. Only we need something like we want to good high energy density or everything we can understand by things with this particular small coin cell. Again, what I'm telling that as an engineering aspect, so at least you can try to develop this particular cell. Or another way is that you can buy the particular big type of pack from the commercial supplier, or you want to integrate into, for example, this battery into your EV vehicles. Again, that's a engineering students, you can do the project again. Maybe I'm going to mention that what are a little bit some safety aspect also you have to understand. For example, you have battery pack. So there is a battery management. Sometimes the voltages you have to vary accordingly. The reason is that depending on chemistry of this particular batteries, always there is a safety limit. Always you have to restrict according to the what are the supplier, or accordingly the we are the depending on chemistry and the supplier, what are the specification you would accordingly have to restrict. Otherwise, so sometimes you may see some safety risks, some fire explosion. Those are all the things you have to take into consideration. So now I think previously what I mentioned that, for example, this particular pack you want to, So they put it in this particular car, any Tesla car again. Always remember, so they use something like 18650. They use something nickel, cobalt, and aluminum doped, like what the layer type cathodes. I'm going to discuss what is the meaning of this particular material in the coming slides. So they use almost like nearly 7,100 cells. So remember, so again the weight of the battery pack is slightly higher. Now the challenge is that how we can reduce this particular number. Of only way is that we can increase the doubling the your energy density or what I call it. So that is there are little bit challenges, and what are the limitation I'm going to explain, especially in terms of the material to the EV market, etc. So now I think what are the important point you to remember. For example, always, so we are looking for any smart material for we have to look for the high energy density and power density. I'm going to explain how to calculate the high energy density or power density of any battery in the coming slides. And afterwards, anyway, high capacity and lightweight is very important. Adapt the climate condition. Again, we have to remember sometimes it may go to extreme low temperature, high temperature, because since there is electrolyte, if you go to low temperature, the electrolyte will freeze accordingly. That's why the battery has to work depending on the temperature. So, and also long cycle life is very important. What is the cycle life? For example, I think people are looking for maybe 15 to 20 years or more. If you get it is good, or you can use the same battery per second life, what they call as a second application, in the sense that, for example, once the battery life is a little bit lower, then we can use it, for example, stationary application like house charging. Those are all the things people can use it for. That's the way in terms of long cycle life. And reliability is very important. Sometimes when you buy a battery pack, so they are mentioning them particular with 360 kilometer per one charge. Everything, whatever the things it has to plus or minus 5-10 kilometer it has to work. Or sometimes the main reason is that sometimes depending on the road conditions or depending on how we are driving factors, this what are the relay, what are the kilometer they told it slightly differences also we can see. Again, I think working voltage I'm going to discuss in the coming slide. At the end, we have to look for high Coulombic efficiency. In the Coulombic efficiency, nothing but difference between charge and discharge capacity. You should be able to get almost like 98 to 99%. If it is huge difference, something so it is not really good. That's why the good batteries say okay. And the impedance of the cell is nothing but resistance of the cell. So what usually it will give the information about is a layman's. So once you before cycling, we can get some resistance. So for example, 10 ohms. After 1 year or like 6 months, if 10 ohms is changing to maybe 50 to 60 is fine. Or the same or this 10 ohms resistance changes to 10,000 ohms or something wrong with your battery pack. So that's why slowly your battery is going to degrade or so soon going to die. That's why this technique is very useful for especially without opening the battery pack. You can see what is the problem with this particular, either what is the problem with the interfaces, or if some problem is there, we can check this particular technique. And again, I think people are always looking for fast charging, in the sense that is there any way to charge a battery within 5 to 10 minutes? So the main issue is that here due to kinetic limitations, because these are solid state materials, so there is a problem with the diffusion. That's why there is a huge particle, some limitations. So that's why we cannot do very fast charges. That's why we have to wait for some time to charge a battery. That's why they each supplier they have some inside there is a battery pack. It will current, everything is monitored with each type of the pack depending on which type of chemistry or which type of battery pack or supplier, etc. After doing all this one, again, we have to look for more safer materials, low cost. I think cost is a very important point you have to remember, and no toxicity. And the end, always you have to look for sustainability in recycle. It's not like we cannot throw the battery in dustbin. Again, you have to recycle, either by you can use it for the secondary applications, or you would like to use the same material. You can use the freshly if you refabricate, or another way is that just you put some other way, some other chemical, just you recycle the different type of elements, etc. And I'm going to discuss in the last if time permits. So in summary, how the battery cycling and what is the mining process it will occurs always usually is a mining and processing. That's why, so always we or the people have this particular, we need a raw materials. That's why we will do mining and processing. The important battery, we need something like lithium, nickel, manganese. That are the important elements, especially for electrolyte and then cathode fabrication. Again, anodes, we have to look for something like graphite. I think graphite also we have plenty, especially. So Again, another thing is aluminum current and stainless steel current collector, especially we need it for cell manufacturing. Another important point to remember, neodymium dysporium, these are the permanent magnets for electric motors again. So these are also very important. That's why, so always remember this type of raw material, for example, rare earths, like China, they have a lot of huge rare earth. There are some cases. That's why some particular thing, some raw materials is dominated by a particular country. That's why, so nowadays people are looking for, so whichever the country they have particular this type, all type of minerals, I think they can make like what they call monopolize the market, etc. Again, afterwards, usually best way is the mining and processing and characterize. You always do testing and manufacturing and then use and recycling. I think this is the way it will work. So in summary, people want to know that something like usually presently cathode cost is slightly higher when compared to your anode and other part like say, including that separators, electrolyte, etc., current collector, etc. So now I'm going to briefly, so what I mentioned that more little bit more in depth how the components I discussed again. Already I mentioned the cathode is a positive electrode. It contains, for example, lithium containing metal oxides, iron phosphate or something mixed with some binder and then conducting carbon they coated on the aluminum current collector. Another side is anode, whereas, for example, graphite mixed with some binder and then finally coated in the copper side. Remember, copper is a very stable to lower voltage, but especially higher voltage if you consider aluminum is good or stainless steel, etc. Usually, most commonly aluminum is used. Inside, we need a separator to avoid the short circuit, the color polypropylene separator. And again, always remember that ions move one side to mode, lithium containing electrolyte is needed. So these are typical cells. So it is always these are the important components, and then sometimes I'm going to explain the how the principle during charge discharge or what is the mechanism with the coming slides. And these are important point to remember. Charge we call as oxidation, sometimes or anodic scan. If you are on positive current, sometimes your battery engineers we call as a state of charge. Again, same thing. Discharge is also reduction. If any oxides are oxidizing, it has to go to reduce. And cathodic scan, negative current or DOC, etc. And these are the things already I mentioned that the purpose of binder is material is going to stick on a current collector. That's why the composite we call as a composite means this way is very important. We mix with these particular oxides, either nano, what are the materials, mix with the binder. At the end, we can call as the battery people, we call as energy storage. Composite means like this. These are the composite of the either binder, conducting carbon, etc. So usually I'm telling this since the workshop is a composite, so that's why especially energy storage composite means so we have to mix with metal oxide with the carbon and PVDF, and this is a composite and finally coated on the current collector either copper or aluminum foil. And typically the composite electrode looks like this way, and then you can do, so you can do, you want to charge, discharge, everything you can do. Again, similarly, if you talk about nanocomposite for electrolytes or, for example, solid oxides or solid state battery, they use this type of, again, we can use this type of, again, the concept is a composite electrodes. So now I think these are the important 2019 Nobel Prizes given to one of the well-known physicist and chemist, Professor John Goodenough. I think he's almost one of the oldest Nobel laureate. I think this year he's turning 100 years. So, and few others also contributed this one. And then in addition to this one, Michel Armand also from French chemist to play an important role in the early discovery of this, but especially intercalation concept or the lithium battery material, etc. So now I'm going to introduce how the principle of the batteries. Again, remember, so already I mentioned that battery contains the positive electrode and negative electrode. What will happen during charge? Lithium move from the cathode to anode, where the electron will pass to the external circuit. During discharge, again, lithium will go back to the cathodes. That's why we call it the rechargeable batteries. So this is a typical cartoon. So if you do same thing, if you plot with, for example, current versus voltage, means simple cyclic voltammogram, you can apply the, for example, at a scan rate, and you can remove the lithium from the structure. The voltage will develop, for example, 3.9 volts. We call it a charge, oxidation, and reduction, etc. So this is a typical reversibility, what they call as a rechargeable batteries. You have to get a positive current and negative current clearly indicate these batteries are rechargeable. So typically, the another way is the voltage of the versus capacity. For example, depending on the chemistry of this particular cathode, 1, 2, 3. For example, depending on the oxides, we can the voltage will be we can get difference in the voltage, as well as the capacity. So energy density, always people are talking about high energy density is nothing but difference between the top charge voltage minus discharge of the cathode minus anode. So always say typically you have to get a huge higher difference between the charge and discharge potentials multiplied by what are the capacity value. That's why always you to think that if you want to discover any, for example, you want to reduce the cost or you want to improve the energy density, always you to if you have any new ideas, if you presently I think we have 200 milliamps we can go. So if you have any new things to double the capacity, they're really challenging, and then we can get another Nobel Prize, etc. So what are the important mechanism? Since suppose, for example, that is very simple style, and at least at the end, since we are in academic research, so for example, any engineering students are want to publish in a specialized journal or irrespective, either engineering or science journal, I think depending on the oxides or what are the materials, we have to write a proper mechanisms. So always, so most commonly we use something like a lithium cobalt oxide, your layered cathodes, or your graphite, or some metal oxides are the intercalation to intercalation. Remember, these more popular. The reason is that we don't see much structural volume variation. That's why it is same aspect if you talk about your alloys or super alloys. Again, we don't see much structural minimum volume variation is to happen. That's why so during the cycling. And for example, you talk about silicon, again, we have something like concept we call alloys. So we call it the say lithium tin alloy or a Li 4.4 SN or Si. These called as alloy forming elements. The advantage of this one is that we can get reduction as well as forming alloys as a consequence. We can get a huge capacity. Advantage of, for example, silicon, if we all familiar, the silicon has advantage, especially improve the capacity. The main issue is the alloy forming element. So there's a volume variation. We need the nanomaterial. If you don't have nanomaterial, we don't have a proper carbon matrix, then what they call a capacity will like we can get capacity slowly degrades. That's why. So they especially here nanotechnology will play an important role. Another area is some metal oxide. Again, there is a lot of interest, especially we can do lot of extensive work, including the many researcher, including our group have been done. The problem here is that although we may get some good capacity, the major issue is voltage hysteresis. So this may not be really good for to make a practical cells out of this one. Anyway, another type of alloy forming elements, again depending on the voltage, we can call it the conversion reaction, etc. So now I think again, what are the important, the brief summary is that if you want to do any either engineer or scientist, what are the important points you have to consider? You want to design a new materials. Always you to look for a low atomic weight or formula weight. It is very important. So theoretical capacity is being calculated by using 26,800 number of lithium divided by weight of the material, for example. Again, ideal anode, you have to get a lower discharge potential is very important. So that's why I already mentioned that charge should be, cathode should be higher charge potential. Voltage of cell is nothing but difference between charge of the average potential with cathode minus anode. Anyway, depending on your chemistry of this particular materials, accordingly the voltage is going to vary. And also, so depending on the capacity values, the energy density is going to vary. Another important point to remember, for example, once you make a cell, we are using electrolyte, so it may not either cathode or anode won't react with soluble with the solvent in the electrolyte, so it's very important. It means chemically stable. And also we have to look for something like a cathode good electronic mixed ion conductor, in the sense that, for example, people are looking for fast charging. For that case, we need something like to pick the current pickup. We have to look for the conductivity. This is very important point to remember. So in summary, what we learned, because that's why they're very famous, because of the high energy density and gravimetric energy density, and also voltage wise is slightly higher if you compare with lead acid or other type of things. That's why this, especially for lightweight applications, people are using. These are more popular, and also space and drones, etc. So still, now it is very major challenge is that, especially for still, so look for the EVs or anything. Again, the cost is a major, and then safety to other point also you take into consideration. So now quickly I'll go through the material processing and fabrication technique. This is very important as a mechanical or any material always you have to we need appropriate for example so for example lithium containing material or transfer metal oxides are depending on something either oxygen and phosphorus are very important materials, especially again we have some lot of materials also we've been screened during the last 15 to 20 years during my thing. So due to time limitation, I'm going to explain some few important materials and also that will be useful for the practical applications. So again, it is very important as any mechanical engineer or a metallurgist or a material process engineer, always you have to look for the what type of the applications. Either some people are looking for catalytic properties or some people are looking mechanical properties or sometimes they, for example, electrical, thermal and magnetic and optical, plasmonic or etc. depending on applications. Identify the candidates. It's not like one material, we cannot use it for the all application. Remember that one. So again, the composition structure, I think depending on the size and shapes, you can vary. And then again, we need appropriate material processing and carry is very important. It is not like one technique is useful for all universal. That's why we need depending on the application or depending requirement, we need appropriate material processing. And again, it is very important you have to know we need appropriate characterization technique to before doing any applications. I think term sometimes nano means like especially our case maybe we are 1 to 100 nanometer and above 100 nanometer is we call as the submicron size materials. I think all people are familiar about the nano. Say the word is nano is anyway everywhere depending on the context. Again, if you talk about energy storage, again the advantage of nano sometimes people want to be fast charging. So there we can what they call lithium diffusion is easier and also we can improve the rate capabilities etc. So any other applications of nano, as you can see, not only batteries, they're everywhere. I think the first functional materials, we can use it for the various energy and environmental and different type of the applications, aerospace, etc. So now related to the materials for energy, again, we have capabilities. I think people as a material researchers, we can produce the materials either by different in the shapes, either nano or some micron size material, depending on the appropriate material methods of preparation. Usually, for example, since for the batteries, we need something really tons of the quantity, not like milligram research. Once you go to industry, I think people have to produce in tons of the again. So they will use something like chemical methods. So for example, co-precipitation there already demonstrated there are some cathode materials people are preparing in tons of the quantity in some industries. And especially for example, another technique, for example, you want to be all solid state or thin film batteries, we need something like physical deposition techniques, or you want to be something like coating techniques or something like atomic layer deposition technique, very useful tool. You want to protect the surface of materials, or you want to be microelectronic applications people can use. And again, plasma, these are the CV, these are all techniques. For example, silicon wafers, you want to reduce, people can do and 3D. Again, as a mechanical engineer, since our, for example, we want to another is solid oxide fuel cells or all solid state batteries. In addition to the nano size, I think that we need a proper contact, particle to particle kind of means we have to look for good mechanical properties. Best way, only way is that we either you can press the materials in turn by hot pressing, or nowadays we have something like additive manufacturing. I think these are all the things and are spot plasma sintering techniques. So idea is that we can use any composite or we can make a really hard what they call we can make into particle to particle intercontact we can get by using this particular technique. So again, I'm mentioning that it is like for example depending on the research area accordingly we need appropriate technique, not like so you have porous materials are there, we can't if we don't have a good mechanical property we cannot do mechanical property. That's why, so depending on the applications again you have to use. And then for example people they use ball milling approach. For example, you want to make any composites or you want to mix nice mixing etc, if you use for mechanical ball milling etc, that is very useful too. So now quickly I'll go through, these are all the things that people are familiar. I think previously people have discussed, or maybe some people are going to cover on what are the useful characteristics. Again, the X-ray technique is very useful tool for us. So you would like to see what type of phases are there, or lattice parameter, and sometimes you have impurity phases. Especially batteries, you would like to see how the what they call cation mixing, lithium is going to transfer metal ion sites. These are all things we can understand. I think we need to appropriate softwares. Either there are a lot of commercial softwares are available. So later you want to be more fancy techniques. Also you can do either neutron, X-ray absorption. There are all things you have to depend on the either by synchrotron facilities. We need to or apply for some beam time, etc. Thin films, there are RBS and nuclear reactions and OSHA. These are all the useful tool. Suppose people are doing with thin film technique, these are very useful tool. Or if want to be XPS, we want to see the oxidation state, or sometimes there are chemical analysis, etc. Especially chemical analysis, especially bulk material, this technique is really good. So again, another technique, I think IR Raman, there are useful tool. Magnetic properties, if people are looking at TGA, DSC means thermal analysis, or sometimes your mechanical people are looking for mechanical properties, again mechanical analyzer, etc. Again, surface area, density, and especially for battery researcher, we need something galvanic potential start or impedance analyzer is needed. Again, I think in the morphology, these are all the common techniques people can use it either any type of the engineering, either mechanical or material engineers. I think nowadays, especially we can do very fancy tech or good techniques or in situ. We want to real time how the battery is going to happen. We can understand the structure. That's why that is a very useful tool. Yes, and some other technique, especially solid state. They're all things we want to do more depth. Still, we can do our research without doing any in situ. For example, with ordinary XRD or SCM or some other technique. For example, surface area, density of the materials is very important. So these are the what they call a fast charger and some impedance analyzer. I'm going to uncyclic voltmeter. What are the use? These are all tools are needed. Suppose especially for battery research, there are including that if you have composites you are preparing, you want to see the conductivity, etc. These particular tools are very useful. So what is the fast charge? It is nothing but I think you usually, so what it will do is that it will monitor the voltage with like lower limit and higher limit, and it will how much, for example, we can calculate by knowing the time and current. We can calculate by mass. We can calculate the capacity, etc. And also we know what are the voltage expected. Accordingly, we know which is higher, what is the energy density expected, or based on the power density, etc. We can calculate power, like current voltage into current, we give the power density. So in summary, what information we are getting, we can get the information about the energy density of the particular batteries. We can carry using this particular technique, or if you want to go for power densities, then the voltage into current, and this voltage into capacity, etc. So there's a way, the different terms we can get, and these are very useful tool. You want to design any battery pack or any type battery, these are very important you have to remember. Another point you already mentioned that how to calculate the experimental time into current by weight of the active material. Theoretically also we can calculate based on this particular formula. And another important thing, once you make a cell, you have to always have to be remember this called irreversible capacity. You have to get a minimum. It is not, for example, this case is too high, it's not really good. For example, here is reasonably good because of the lower irreversible capacity. If you compare your fuel air graphene, again you get higher ICL when compared to your other things. So it's very important you to remember always you to look for a lower ICL. And capacity fitting is nothing but, for example, second cycle minus n cycle, like 100 or whatever the number you can put, divided by second cycle, we can calculate capacity fitting. Coulombic efficiency, I mentioned the difference between charge, discharge minus charge. Accordingly, that's why I told you that we have to get a lower reversible capacity, etc. So again, I think people may ask you what are the rate capabilities. For example, there's a 5C means like in 12 minutes total energy. That's why. So in a particular battery pack, there is a different 0.1C means like nearly 10 hours charging. So this one is like 1C means 1 hour. That's why usually, for example, this particular battery pack, they don't go very fast charge. The reason is that you may get lower capacity. In order to retain that what are the reasonably good capacity, they have some particular battery inside the software, inside the package. They can tell, they fix the current, and then everything. The reason is that, remember, these are the particles depending on a particle size, and then we can, there is a problem with the mass diffusion, mass transport. For example, bigger particle diffusion, due to diffusion limitations, that sometimes all particle may not be participating in electrochemical cycling. We may not get higher, what are the capacity. That's why you may get a lower capacity. That's why As the industry, depending on the particular, they want uniform particle size and nice conducting matrix, and so at the end they will tell that okay, you have to use this particular material, this much current, like that way. So that's why it's very important how to improve that one. Only way that now use of the nanotechnology, something like nanoporous materials design. And another way is to improve the electronic conductivity, means you coat the surface by something like carbon coating or graphene or some other type of the coating you can do. Another way is electrode design, current collector modification, or appropriate electrode kinetics. So it is very important, especially thickness also very important. Sometimes you be too thick is there's a problem with the diffusion limitations. Sometimes they need something like uniform. Too high is also not good. Too thin. Sometimes you usually they are making compromising with the thickness also. So again, another the voltage cyclic voltammetry. We want to see that predict the voltage again. So we want to see what you are getting from the galvanostatic instrument, and we have to see how the charge and discharge potential or redox potential. Usually, we are going to fix a scan rate, and accordingly, your materials we can see. For example, depending on the materials, you can see the 4 volts, 3.5 volts, etc. Again, it will vary depending on which type of materials, etc. We can get the information about this one. So again, suppose contact fuel or the supercapacitor, again the carbon-based system, we can get rectangular, or if we have metal oxide, we can see difference in the curves, etc. We can see these are all the use of this particular technique. Now I'll go to another last technique, especially the impedance. So that later I'll spend quickly go through some few examples. So this is also a very useful tool if you have composites also there, or you want to study something like impedance or response of the cell. And this particular tool, if you want to make a pellet and try to coat in either platinum or gold, then you can make a for example, you want to be heat. This similarly same thing applies to you want to be resistance, response, everything, or your phase change, anything, any type of materials you want to see the electrical conductivity, etc. You can understand this particular techniques. So only that you want heating or cooling, accordingly we need a respective another apparatus to you need to monitor this temperature, etc. So these are the advantages of this particular technique. I think all people are familiar with not only batteries, solid state ionics or chemical sensors, photoelectric solar cell, fuel cells, etc. Not only this area, and also people are doing something like biomedical, etc. This particular technique. The idea is that we want to understand electrode-electrolyte interfaces and diffusion rates, and also we want to understand the electrode kinetics, etc. So either you can do something like 3 electrode system, or for example, 3 is a 3 electrode system, or usually practically we do something like 2 electrode system we are going to use. Either you can do sodium or any type of the like what example batteries also you can do the same technique. So if it is solids, again, so you want to be something like ceramic bulk material, you want to see grain and grain boundary resistance, etc. Or we can separate it out by using the appropriate, for example, we can with the appropriate model, we can calculate this what type of resistance we are getting accordingly. We can segregate this with respect to temperature, we see the grain and grain boundary resistance, etc. I can do by this particular technique. So in summary, so advantage of this particular, if you make a real battery as a liquid-based system, you can get some surface film resistance and different type of resistance will come. That's why there is a lot of interest. So the same thing what we learned from the electronics in during your engineering classes, if you go for higher level, the same apparatus, people depending on your expertise, people can use it this particular technique in a different aspect of the especially applications, either batteries or your thin films are there, you want to see the homogeneity of thin films, or your thin films is rough or smooth. Again, this technique is very useful to understand this one. So anyway, due to time limitations, I don't have much time. If people or anybody is interested, feel free to contact me. Then again, I'm happy to discuss more on this particular technique. So either again, you can do something like a different, depending on voltage, etc. You can do something like complex modeling. And again, you can do either resistor, capacitor combinations. We can do this. So now coming to this bigger pack, what are the opportunities? So if you take a little bit bigger EV electric vehicles, again, you make a big packs. Again, there is a lot of, you can see that. So for example, you can see this, there is a power electronics and electrical. For example, electric machine, again, there is a lot of contribution by the automobile or mechanical engineering department. Again, people are working in this one. Again, energy management and battery management, again, we have to suppose in terms of material level, we have to work with the material engineers or chemists or whatever it may be. Again, energy storage, system engineering. That's why again, what is the way? So that's why there is a lot of interdisciplinary. All people have to work together. So again, there's a lot, especially you want to understand this one. That's why it's very important to. It is a multidisciplinary area of the research. So now, due to time limitation, since my time is almost for 48 minutes, I finished nearly 50 minutes. So I'm going to explain some few examples. So how to, so what are the important components of cathodes and anodes? Always remember, presently, I think we have something a little bit advantage. Anode side ways we are able to go slightly higher side, especially for cathode. There is this problem with limitation in terms of the capacity. That's why, so we are not able to extend the energy. Still there is a lot of challenge. That's why, so there is a scope. We have any good ideas. People are looking for high energy density cathodes that will be very useful. That's why there is, although there is a one lot of interest in the, especially on academic researchers, we can contribute in a different way. That's why it is especially for young researcher, we can do, we can think in a different way. At least we can contribute something a little bit, improve the energy density of this particular material. So especially other aspect is, for example, if you're engineers or mechanical, they sometimes we know that all people cannot think in a new thing direction, or some people they may take existing material, they can to improve something like surface coating, just protect the surface, what are the capacity we are getting, or at least we can use that one, and then they can use this particular material by from either by industrial supplier, or they can try to fabricate themselves, and try to understand that how they improve the energy density in a different way, either electrode design or in a different type of the electrode packing, or what is the different electrode technology, etc. So these are the, in terms of the positive electrodes, again, these are popular is NCM, is nickel, cobalt, manganese. 8 means 80% of nickel, 10 like that way. So always remember, depending on the more nickel, we may get good capacity. Again, accordingly, we need something like these are the redox couple. And if iron phosphate is, iron is a less expensive materials. Again, uh, 2 plus to 3 plus is a redox couple. There are important points to remember. Accordingly, we have to get the different type material. Anyway, due to time limitation, I'm going to explain one example. Again, these are the usually we can try to prepare by using the carbothermal reduction method. So some metal oxide, for example, iron phosphate, lithium iridium fluorophosphate. There are a few lot of oxides, are simple to complex oxide, and I don't have time to discuss to. So what I'm mentioning that you try to mix depending on the initial reactant. If you want to reduce to higher oxidation, lower oxidation, accordingly mix amount, calculated amount of carbon, or slightly some 10% excess also can do. And finally, we can reduce it. And at the end, sometimes you want to use some graphene oxide, again, RGO, we can, in reduction, we can see some carbon coating also. So this is a typical furnace. Either you can purge with argon gas, or you want to be nitrogen or ammonia, we can get some respective nitrites, etc. Again, by playing the temperature, we can, are too much carbon use. Sometimes you may get some metals dispersed in carbon matrix. Suppose this is very important. People are looking for catalysis, some other type of the applications. So this one particular example is lithium, and this is a real cathode. Again, we have to look, always remember, we have to look for vanadium 3 plus to 4 plus. These are couple expected, and these are theoretical capacity. So always remember, so phosphorus oxygen bond is a little bit could be compared to the metal oxygen bonds, and also thermal stability wise is a little bit better than your lithium cobalt oxide. So again, we can prepare the sample with either then we characterize them XRD and some other techniques just to see how the crystal structure is okay or not. Again, and with a particular software, we can get to generate the lattice parameter, etc. And finally, once it's ready, for our applications, we need a composite electrodes. You can try to make either by cathode anode all together. Finally, coat by using some ductile blade. Finally, it looks like this way. Again, dry the things and roll it, and finally we can make a popo, like for example the cylindrical kind cell, or you want to make a big pouch cell, depending on the whatever the way you can cut it. And finally we can transfer this one into the this particular glove box. This is ready. So this is ready. You can try to fabricate in a small cell or bigger cell, whatever the cell. Only thing remember, accordingly, if it is a bigger battery fabrication, we need a bigger dry room or bigger glove box. That is the way industry people can do. For example, the usually industry, like for example, previously my our thing, and also we have this a lot of big facilities. They can make a cell, everything is an automated. Again, only thing is we need a lot of money and also more space. Again, it's a little bit bigger program. Only we can do either by collaboration with the industry or sometimes national laboratory who have with all sophisticated facilities they can do. So usually that since we are academic researcher, we want to see that how this coin cell performance, you can try to fabricate this cell there, coin cell, put separator or lithium or for example graphite for electrode can do. Finally put top cap and finally the cell is ready. Either you can do either fast charging or slow charging, anything, whatever the way you want to do, you can do the testing. So typical way they can tell the charge and discharge potential is the cycle number, for example, capacitor cycle number. Finally, depending on your cathode, one, for example, the 3.5, 4, or 4.2, depending on the material. So again, automatically you can see among 1, 2, 3, you may see that is higher voltage, you may expect higher energy density. So again, I think this is the way we learn from this particular coin cell. Again, the same material, we want people as an industry, they can prepare in large scale and they can do scale up, and then we can do whatever the design they want, they can do. There's a lot more on engineering also you can do, etc. So again, you can do as a researcher, you can do something like how to see the structure is material is good or not. Either you can do XC2 cycling or impedance, etc. You can do. So again, I'm repeating, remember what we learned from this one. Always make sure that if you good cathode, higher charge potential, and also higher capacity as a consequence, you want to get higher energy density or capacity. So that will be good. So now I think since, so I have another almost like 55 minutes I finish. So again, so few other materials also, some novel materials we will look in, because apart from the research is to grow. So these are the new example for early report we've been reported. So advanced, for example, the metal organic, inorganic complex, because you may get some 3.5 volt materials. If you compare your this particular new compound, you can nearly 4 volts we can get again. So accordingly, so we can get in terms of energy densities. Still there is a challenge. So capacity wise was a little bit lower than as we expected. So that's why, so either you can do some simple, either by chemical processing you can do, you can try to get, and finally we can get rid of the water by using the heating the sample nearly 150 degree, and you can characterize them with the various techniques, standard techniques already I mentioned with XPS and then SCM, etc. I can do. So good way as a battery researcher, always you to look for the 4 volts means higher energy voltage wise really good, and also so so also slightly lower expected, I mean in terms of the commercial range slightly lower. Still there is a lot of scope for this one. We can reduce the either by reducing the particle size, or for example we can do lowering the atomic weight, and automatically we can get the higher capacity, etc. So you may ask you, what about lithium? Why don't you work with the potassium or sodium? Again, our experience also we did with the other one. Based on the mobility, we know that lithium has a lower ionic radius, followed by sodium, potassium. So if you go for higher, sometimes the mobility issues, sometimes capacity was little lower when compared to your lithium. So again, still there is a lot of some of well-known people also, they've been taken to this particular compound and they will improve further by using electrode optimization or material synthesis, etc. So and also some few example, again this early report followed by some including a noble laureate also we've been looked into our system either by sodium or the same materials in different type of synthesis also have been done with the different others. So again, similar way you can try to get a different appropriate chemical processing techniques. You can try to prepare what are the scale up also is possible. Usually as a we have to get to 4 volts and also really good reversible peaks we can get by using this particular thing. So again, there is a possibilities you can do phosphate, either you can do a different type of sodium, lithium, potassium. And still we feel like lithium seems to be good, better when in terms of mobility issues compared to your other things, and followed by few other things also by other literatures. People have already been done some extension of this particular work. So now I think people may ask you that again, for example, so lithium we cannot depend on other. So sometimes there is a possibility sodium. Yes, sodium is also is a old technique, not really. So you see that before lithium battery existing, the sodium compounds and at the time. So we know that sodium can move from this layered compound. Only problem is that these compounds are hygroscopic and stability wise, and also voltage wise slightly lower. So as a consequence, we can see that, for example, these are different type of the materials we have. And especially if you talk about the sodium lithium system 4.2 volts, we can get either sodium, we can get 3.5. And as a typically as a layman, here we can get slight ion energy density, and we can get lower energy density in case of sodium based system. Irrespective, I think we would compromise sometimes per grid storage. Again, their cost is also very important. That's why still if you do sodium technology, we can reduce 20 to 30% of the overall cost of the particular battery. Always remember battery, it is not only lithium things, also other aspect. For example, EV, we need something like rare earth and something like all this ones. Not only, so that's why if whichever all the elements, the raw materials they have, so we can reduce the further cost of the batteries. Anyways, some other people may ask you that why don't you use organic something because naturally occurring green and sustainable. Yes, it's possible. The only problem is we don't get higher voltage wise slightly lower when compared to your inorganic based oxide. That's why we don't see much not much practical applications. So another important point you have to remember, for example, another the second part of my presentation, maybe another 20 minutes, I'm going to discuss briefly. So what are the important, what are the real challenges here? So presently, the most common material we're using the graphite because the reason is that graphite is a lower discharge potential and also is a naturally occurring. Either you can do petroleum coke, also you can extract, you can produce graphite or artificially can get or naturally, say, for example, we can get from the rock. That's why here in Quebec presently our company they're producing a lot of graphite mining from graphite rocks. So that's why, so depending on the there is an interesting source with including India also we have a lot of carbon containing source. Again, silicon, these are the other things we want to improve the capacity. People can use mix with some silicon, something 10 to 5 to 10% of silicon to graphite so that we can get extend the capacity, etc. Anyway, some other materials also there. I'm going to briefly what are the, so in summary, again, I'm talking about always you to look for the applications, always you to think in terms of the lower discharge potential. That's why graphite seems to be more popular when compared to your other graphene or fully graphene or whatever it may be. So among the most popular is the graphite. Okay, still graphene we can use only if you want to coat the some what they call conducting coating or something like current collector, improve the current collector we can do. So people may ask what are the other applications, graphene, graphite. Again, I think all people are familiar. People can use it for paint and refractory and then fuel cells and different type of things. For example, depending on all the areas, not only mechanical engineering, sometimes people are talking about green concrete. They use something like some carbon fibers. They use something like very strong bricks. So you want to get refractory material, etc. They can do. So regarding anode materials, what are the real things always people are think to improve the, for example, rate capabilities? One way is to improve the nano size materials. There is a one thing. Another one is a matrix element, for example, alloy forming elements with a way, and use of something like some conducting coating, for example, zinc, so for example, vanadium oxide or ruthenium oxide, or graphene. So these are the conducting material, or sometimes we may use something like alloying and conversion reaction, alloying and conversion based oxides. So usually as a researcher, we need something like tools since the new materials always you to look into the XRD, SCM, etc. Finally, based on this particular technique, we need to we need appropriate techniques, and then finally, for example, alloys. These are this alloy here the lithium, aluminum, silicon alloy, tin alloy most commonly. So these are that's why we are high capacity materials we are going to use, and we have aluminum, indium. Still, they're not popular much. So again, so I'm going to discuss about few example on tin based oxides and how it looks like. Again, these are the small contribution from our group. Again, so red belongs to our group. So again, there is a lot of new material. Among them, this only bunch of new materials are available. Still, there is a lot of scope. So people have looked for some new material. Again, here the challenge here is that how to reduce the voltage, especially irreversible capacity in the first cycle is a little bit challenge since the oxides from Li2 in the first cycle you have to take into consideration. So again, the discharge and charge potential should be around 0.25 and zero point 0.5 like that way in graph. So again, I think use of something like that. One example, if you take about nano and submicron size, again the importance of nanomaterials seems to be in terms of rate capability, it will be good. Stability wise, some submicron size you can do slow capacity fading. So reason here is that you know that like vanadium or cobalt are nice electronic conductive materials. So if you do long-term cycling, they are more stable in terms of resistance. What you are getting from the initially, at the end of 100 cycle, the resistance is almost same. Clearly indicate that. So these are the better matrix element for the lithium cycling. I think I'm going to similar concept also. We can do some hollandites. There are the very complex oxides. Or you can do indium, cobalt, and indium. Again, you can do ceramic materials, or I can do ball milling. We can reduce the nanomaterial by using the particle size reduction. You can do ball milling, etc. I can do. So these are the few example. If you the importance of the matrix element again. So how the rate capability, especially cobalt, seems to be good because the cobalt is nice electronic and similar to the your vanadium. So again, there's a lot of bunch of other oxides. Say, for example, you see that anode-based material again. There is a lot of interesting things people can do other oxides. So major challenges for the battery, we have to look for the reduction of the charge discharge potential lower. Seems to be good. Then only we can use it for the practical applications. And still we can do as a researcher or a material researcher, you can do something. Either you can different type of the opportunities are possible. So same thing if you want to do with the sodium lithium again with respect to you can replace with lithium by sodium again. Accordingly, we can get difference in the voltage potential or energy density. Also, we can see the difference in the capacity, etc. Again, this alloy forming element you have to remember always to think about the voltage. So slightly, although we get higher voltage, we get higher capacity. Sometimes capacity will fade depending on the things. You have to restrict the voltage accordingly. What are the better operating voltage, etc. I can do. So these are all things only learn more depth once you slowly do what type of system, and then once you get the information and read the literature, you can get the all the good information. So I think I've already. So what are the important points you have to remember? Suppose you can do either oxides. You can do. Why don't you use nitrate? Yes, it's possible. So reason if you take nitrites, we can get 3 lithium, whereas oxides only 2 lithium. So the theoretical limit. So anyway, still we our experience we few example we consider in terms of nano seems to be here good, followed by bulk and then our experience something like hard metal, titanium nitrate, chromium, vanadium. They're a little bit hard and we don't see much improvement in the electrochemical or energy storage performance. So anyway, there is a lot of other things and more popular is the LIT. These are the one material only is useful for the practical or EV. They can mix with high voltage cathode and they can make a full cell out of this one. So one example is titanium based oxide. Again, the TiO2 people can use it for different applications, either electrochromics or solar cells or batteries or sometimes biomedical or paint industry. Again, we need depending on application, we need appropriate particle size, etc. Again, so either different processing already one example with the molten salt approach, you can produce this crystalline material with almost like uniform particles with high surface area material we can get. So you don't need any expensive, for example, surfactant or with simple what I call a mix with some nitrate melt with respective titanium oxysulfates, titanium salt, and put it in aluminum crucible at various temperature you can get, and finally we can get a respective simple pure anatase phase. You don't see almost like single phase materials. Again, you can do with respect to sintering temperature. We can see different in the what they call phase evolution from anatase to rutile phase, etc. Again, people may ask you that there are a few examples. If you go for nano size to micron size, how the energy storage is going decreasing. The reason is that it is more special because easily this intercalation based oxide we need a lower part, high surface area, and also lower average crystallite size is needed for this particular thing. Again, I think people want you can do some small DSSC applications, so you can do just we can see some improvement in the vertical efficiency, etc. So if you compare similarly, if you want to look for the binary tin oxide, also you can do similar approach. You can do either since there are semiconductor materials, you can use either by batteries or if, for example, you want to use it for example, sensor application, etc. Again, you can play with depending on process parameter, temperature, time, etc. I can get the different in the particle size, etc. I can get. So again, some materials, or for example, semiconductor oxide, we can use not only batteries, either you can do some sensor-based materials. Again, we need something like appropriate expertise and some, for example, oxides or composites and silicon type material, because we can use something like electrochemical sensors, etc. I can use. So I think I'm going to say in a still these are examples in some oxides also people want to play with. You don't want to expect lithium battery. Still, you can do some simple electrochemistry with like super capacitor. Also, you can do. There is also another way people want to explore some composites with type of metal oxides. So now quickly I'll go through, maybe so I have another maybe 5 minutes. So what are the important points you to remember? For example, people see that called thermal runaway or thermal stability. People, some batteries are catching fire or somewhere here. So that mainly that is due to that people are taking the flammability of the electrolyte or oxygen release from the materials. Also sometimes the entrance, this is due to, and also other reason like malfunction of electronic circuits. Sometimes these are the reasons for the what they call thermal runaway or the thermal stable battery. That's why we can see catch with depending on the what manufacturing or how their these are the different type of reasons. So typically, again, there is complex. I think fire is coming from electrolytes because their flammability, or sometimes cathode they may go to higher voltage limit. Then there is the oxygen evolution occurs, and sometimes anodes and fast charging also here. It's sometimes it's not good. That's why power fade and especially material degradation, internal short circuit, and we can do, for example, we have to protect the materials like mitigating strategy, and again, for example, cooling. Either you can do phase change materials or some, for example, coolants. Also, you can do. So these are the way different people can do. So in terms of mechanical abuse, electrical abuse, thermal abuse, finally that will lead to the thermal runway. So again, sometimes either due to the deformation of the separator, a lot of like dendritic growth, especially those are all things also taken to leads to internal circuit. And also sometimes temperature, and if you go to high temperature, there is a separator is going to shrink, and the end it is going to be again thermal runway, etc. So again, sometimes it may catch fire and we release with oxygen, etc. So again, the same story. What are the things? For example, cathodes. These are the same thing. What is same story? Already I told them. So either anodes, especially for in terms of the anode failure mechanism. Sometimes the SCI layer, and sometimes it may decomposition due to the runway, or sometimes another way is sometimes rapid charging, and also sometimes due to the dendritic growth. Also, we can see due to puncturing of the separator, it also leads to internal circuit, etc. These are all the important points to remember. Sometimes if you are about cathodes, again the overcharging also, these are all the important points. So that's again that may lead to the thermal runway, or sometimes there is a reaction with electrolyte again. So these are the that will also lead to the thermal runway. And sometimes due to electrolyte, again the electrolyte, there is a safety limit and high temperature things, and also sometimes separators, again separators lead short depending on temperature. Separator is going to shrink, again that will also lead to thermal runway. So again, I think people are adopting something like how to mitigate something like fire and suppression additives people are using. And then, so in summary, these are different mitigating strategy. Again, the people can use either by intrinsic safety, either cathode, anode alteration, electrolyte. Again, safety of devices. Again, the vent, phase change materials. Again, thermal management, air cooling, liquid cooling. Again, the phase change material cooling. Again, you can see there is a lot of interdisciplinary, especially our mechanical engineers. We have to work, especially in terms of people have good ideas about phase change materials. Again, they sense the temperature, etc. I can do that is very useful too. So I think quickly one last slide. What are the importance of in situ? So sometimes people may ask you that why don't we go to higher voltage? Yes, it's possible. For example, this in situ technique is very useful for real time. We see how the with respect to voltage, how is going to vary. So for example, some cases if you go to higher voltage, practically they may stop somewhere here because in the practical cells. The reason is that if you go for higher voltage, we can get the remove lithium from the sometimes may react with electrolyte, and then at the end it may get some what they call as a fire and safety reasons at the end. That's why intrinsically this type some depending on the chemistry of material, this particular battery they have to go to some safety limit. Don't exceed to the higher limit. What are the limit they suggested you can go, or plus or minus 0.2 or zero point 0.1 is volts higher or lower is fine. Anyway, you can do some fancy techniques either by neutrons. There are all things you really don't need. So either you can do simple XRD that may solve your purpose. So, and some other techniques we can do since time limitation. I think last one slide I'm going to tell that since I have another one or 2 minutes. So again, sustainability is very important. What are the research you do to recycle? What is the concept? The reason is that so nearly another by 2048 or 50, nearly 900 million, more than 900 million electric cars by around 48. Again, nearly 11 million metric tons of the spent batteries have been discarded by 2030. Clearly indicate that there is a lot of so if you don't understand this one, if we don't dispose in a properly, especially we lead ecotoxicity, global warming, etc. That's why we have to recycle them in a proper way, especially either by direct and by hydro and pyrometallurgy approaches. In fact, this one is already been done by the industry, especially there is a lot of especially recycling technology. Usual way is that discharging, dismantling, and pre-treatment. Either you can do. That's why you can see these are all again all steps are involving. That's why cost is also increasing because we want to recover all the materials. Again, the cost is going to be higher. So usually depending on the two techniques, I think hydrometallurgy means we need a water leaching agent again. So advantage is that again you have to water you have to recycle, and then for example you again neutralize this by using the since we're using acid. So sometimes people are telling that this hydrometallurgy approach may not be economical. That sometimes pyrometallurgy approach seems to be good because there is advantages. Again, this technology has been demonstrated by various companies within Belgium and also Switzerland and USA, etc., and Japan, etc. So, in summary, one example, if you want to be this particular material, we cannot get lithium cobalt oxide at the end. We can get in terms of carbonate and cobalt metal. That's why if we 3-4 elements are there, again, we need recycling cost is going to be high. That's why depending on which type of the cathodes are around, accordingly, we need appropriate recycling technology. I think these are the small conclusions. Maybe what I am telling the word is I'm telling that still there is a lot of scope. We'll have to look for nano-composites for large scale synthesis, especially always people are talking greener synthesis and then electrolyte materials. And still there is a lot of scope for the long life novel material. And also there is at the end I'm mentioning that always we have to work with both scientists and engineers, especially for large scale uh, battery fabrication. That's very important. Always you to think about the for example you have to collaborate. It's not like one person you have to do. Sometimes the mechanical engineer is one good in one aspect, and sometimes you have to work with the electrical engineers, or you have to work with material engineers or some chemist or physicist. Accordingly, then only we can understand and we can work, especially in terms of students. So that is the way it is a multidisciplinary and there is a lot of opportunity. And thank you very much. So okay, thank you very much. Maybe I'll take some question and answer. So if you have
Dear
so,
participant, if you have any questions, you can ask.
so stop presenting, or maybe I can put my email. So maybe can
Sure, sir. Sure, sir.
yeah, please okay. Sorry, some people have told us some audible problem. I don't know how the internet. Maybe sometimes Yeah, hopefully other people can.
No, no, sir. There is a very much good connectivity. So there is no
Okay,
problem.
okay. Thank you.
Yes, yes, sir, I think there is no questions. Okay, so that we'll wind up, sir. So I would like to thank you, sir, for your wonderful session on the recent advances of nanocomposites in the field of the energy storage. So it was very much wonderful, sir. So that we have enjoyed your talk, and when we'll also hope to continue your contact in further future aspects, sir. Thank you very much, sir. And
Okay, once again, thank you very much. And anyway, especially for the students, if anybody is interested, feel free to send me by email. Okay, okay, I'll try to answer whatever the things I know. Okay, and thank you very much again, Professor Raju sir, also for his
Thank you.
kind,
Thank you. Thanks, Reddy Garu. Thank you very much. We'll
kind
meet you
efforts.
once
Thank
again.
you very much. Yes, sir. Thank you very much, sir.
Okay.
Okay.
Thank you, sir.
Okay. Especially
Yeah.
students, if any, although I'm not doing any some academic research, especially we can try to feel free to contact and then okay. Thank you very much. Thank you and try to attend all the talks. This is very important. That's the way we are learning. And again, thank you very much, sir. Thank you.
Thank you, sir.
Thank you. To it's my already maybe is good night. Okay, for me, good night and then good day.
Yeah. Good night. Good night for you. Good night and good
Thank
day
you.
for us.
Thank you. Okay, thank you. Thank you.
Okay, sir. Google Forum has been shared for you to give your feedback on the session. Please fill it and submit it. Thank you. We'll join at exactly at 11:30 for the second session, which will be delivered by Dr. N.V. Ravi Kumar. He is called as Rarnath Ravi Kumar. He is the head of the Department of Metallurgical and Materials Engineering, IIT Madras. Thank you.
Hello, good morning, Ravi Kumar sir.
Good morning, Professor Raju. I have joined. I just wanted to let you know that I have joined.
Yeah, sir. Okay. So this is Bairegowda
Oh, sorry.
from Dr. Reddy. Okay, sir. Sir, at 11:30 exactly we'll start. You can share your screen at 11:30, sir.
Yes, I will do that. I will do that.
Yeah, sir.
Good morning, sir. This is Raju, sir.
Good morning, Raju.
Yes, sir. How are you, sir?
I am doing good, Raju. Doing good. Yeah.
Okay. We'll start in another 1 minute or 2 minutes, sir.
Yes,
It will be 11:30. We'll start.
I'm. Once you give a go ahead, I will share my screen.
Okay, sir. Thank you, sir. Thank you.
Yeah, thank you.
Amit, are you there?
Yes, sir.
Okay. Tejesh. Yeah. We exactly start at 11:30.
Yeah.
I think now we can start at 11:30.
Yes, sir. Okay. Okay. Good morning, everyone, all the participants and the speaker, Dr. Ravi Kumar NV, sir. So now the fifth session of recent advances in composites and nano-materials. The session will be led by Dr. Ravi Kumar NV, and Dr. Ravi Kumar obtained his doctorate in natural sciences from the Max Planck Institute for Metals Research, Stuttgart, Germany in 2004 with a Sergert grade with a fellowship from the Max Planck Institute. Subsequently, he continued in the same institute as a postdoctoral researcher and guest scientist. He worked on the high temperature deformation behavior of polymer precursor derived ceramics during this stay. After 6 years of stay at the Max Planck Institute, he moved to the Institute for Shock Physics in Pullman, USA, and worked on the dynamic response of bulk metallic glasses for a brief period. He returned back to India in 2007 and joined the Department of Metallurgical and Materials Engineering at IIT Madras as an assistant professor. Since 2012, he worked in the same department as associate professor and heads the Central XRD laboratory. He is currently professor for ceramics in the Department of Metallurgical and Materials Engineering at IIT Madras since 2018. As head of the Central XRD laboratory, he consults a large number of industries both in India and abroad. He has been a visiting professor at the Christian University of Kiel in Germany, Shanghai Institute of Ceramics in China, European Membrane Institute in France, University of Stuttgart in Germany, University of Bergamo in Italy, St. Petersburg University in Russia. He collaborates with a large number of national and international institutes and organizations. His ongoing and past international collaborations include the Vinca Institute of Nuclear Sciences in Belgrade, Serbia University of Montpellier in France, IFW Dresden, TU Darmstadt, University of Stuttgart, and University of Cologne in Germany, Japan Advanced Institute of Sciences and Technology, and St. Petersburg University in Russia. He has been a recipient of the following awards and honors. Recipient of the Institute Research and Development Award for the year 2015, awarded by the Indian Institute of Technology, Madras, and also recipient of the Certificate of Distinction for Excellence in Teaching during the International Teaching Week at Hope University of Applied Sciences, Germany in June 2013. Also is a recipient of the Young Faculty Recognition Award for the year 2012, awarded by the Indian Institute of Technology, Madras, and also recipient of the IEI Young Engineers Award 2010 in Metallurgical and Materials Engineering discipline from the Institution of Engineers, and also is a recipient of the Young Scientist Award from the Indian Ceramic Society, India. His professional experience includes working for ISRO Satellite Center in Bangalore, Department of Space, Government of India. He has published more than 75 peer-reviewed international papers and delivered several prestigious invited lectures in India, Europe, and US. Professor Ravi Kumar has executed several sponsored projects funded by various agencies of the Government of India and coordinating several projects to the tune of 1.5 million US dollar as principal investigator and co-investigator. He is currently executing bilateral projects with the St. Petersburg University and IFE Institute of Russia, Japan Advanced Institute of Science and Technology in Japan, University of Cologne in Germany. His research interests include development of novel, non-metallic and inorganic materials whose properties can be tuned on an atomistic scale, which includes thermal management, catalysis, and energy. He is on the editorial board of the following journals: Surface Innovations as editor, Advances in Material Science and Engineering as associate editor, Frontiers in Materials for Ceramics and Glass as a review editor. Currently, he holds the following institutional responsibilities at IIT Madras. Apart from being the head of the department, he is also head Central XRD Laboratory, member Faculty Council, IIT Madras Research Park, member Board of Industrial Consultancy and Sponsored Research, IIT Madras, member Board of Training and Placement, IIT Madras, member Board of Global Engagement, IIT Madras. Under the Institution of Eminence scheme, Professor Ravi Kumar is a part of the new Center of Excellence in Materials and Manufacturing for Futuristic Mobility with a budget overlay of close to 15 crores and is the lead coordinator for the Ceramic Technologies Group. He teaches mechanical behavior of materials, brittle fracture and identification mechanics, materials under extreme environments and X-ray diffraction techniques for graduate students. At present, he is leading a team of around 20 people in the Department of Metallurgical and Materials Engineering at IIT Madras, Chennai in India. Welcome Ravi Kumar sir. Hello.
Good morning, everybody.
You can start, sir.
Yeah, good morning, everybody, and thank you very much for the very long introduction.
Yeah.
I didn't expect that you would be introducing me completely based on the CV that I sent. But anyway, thank you very much, and thank you very much, Professor Raju, for inviting me, and thanks to Ambedkar Institute of Technology for asking me to give this talk. I'll start sharing my slides, and let me know if you're able to see the slides.
Yes, sir, sure.
Yeah, can you see my slides now?
Yeah, now it is visible, sir.
Okay. So if my slides are visible, let me get started with my talk. And my today's talk is on.
Hello, sir. Can you make it a full screen, sir?
It is in full screen right now.
No, it's not coming.
As far as I'm concerned, I have put it in full screen.
Okay.
It's still not in full screen for you?
It's not full screen, sir, still.
But I have actually put it on full screen already.
Okay. Anyway, it is visible. You can continue, sir.
Yeah, if it is visible, then I will continue so that there is we don't waste any more time. So today's talk is focused on some of the advanced ceramics and ceramic matrix composites that are considered for automotive and aviation sectors. As I was introduced, I am currently heading the Department of Metallurgical and Materials Engineering at IIT Madras. And very recently, I'm also coordinating the Center for Materials and Manufacturing for Futuristic Mobility. I'll just briefly tell about these things before I actually go to the scientific topic. Before I go to the scientific topic itself, let me tell you what we do in our lab. My lab is called Laboratory for High Performance Ceramics. So we develop ceramic materials for high performance applications. We have 3 applications in mind. We look at 3 aspects. One is security. That means we look at material development for defense and aerospace sector. So we collaborate a lot with Vikram Sarabhai Space Center in Thiruvananthapuram. And we also work on energy. So we do involve ourselves in energy production and energy storage. So for example, on the left-hand side, you can see solar thermal splitting of water. So what we do is we develop materials which can split water and where we can produce hydrogen, because hydrogen is something that is required for green energy. So if you are looking at replacing fossil fuel-based energy, then the next immediate option for us is hydrogen production. So you can already imagine some of the Western nations have already moved to hydrogen cars and so on. So that is one of the topics that I work on. We are also working with some of our Russian collaborators to develop materials for capacitor-based energy storage devices. So that is as far as the energy part is concerned. And as far as the environment part is concerned, in recent times we have not been working on, but a few years back we did work on freshwater remediation, water remediation and working on freshwater crisis. So basically, looking at contaminated water and how to use ceramic technologies to make contaminated water clear enough for us to utilize, for human beings to utilize. So this is a very important topic because environment is something that we leave it for the next generation, and it's important to make sure that if there are any already polluted waters, to see how to make these polluted waters back to usable state. So these are very important aspects. Our lab works on developing materials to solve this. So as I told you, IIT Madras became an institution of eminence, and under this scheme, we have started a new center called Center for Materials and Manufacturing for Futuristic Mobility, and I am the lead coordinator for that center. And it has close to around 45 to 50 professors from various departments who are participating in that center. And in that center, there are 5 different verticals, and one of the verticals focuses on ceramic technologies, and I'm the lead coordinator for the ceramic technologies for that vertical. And along with me, Professor Sanjay Mathur from University of Cologne in Germany, and Professor Alexander Mihalis, who is managing director of the Fraunhofer Institute for Ceramic Technologies, are also main partners in establishing this center. For people who are interested to look at the activities of the center, you can look at this website, www.ctfm.in. So basically, it's called Ceramic Technologies for Futuristic Mobility. So ctfm.in. So you can have a look at this website, so you get complete picture about the national team as well as the international team who are participating in this center. So when we look at materials research, I think I don't know whether the audience come from a strong materials background, but ours is a materials department. So we look at what are the challenges in materials research. If you look at challenges in materials research, whether it is India or any other country, most of them are interested in materials research that is related to security and environment. So that is what ultimately it boils down to. Because everybody wants to have a secure life, and everybody works on research topics that has to do directly with security. So hence you can see even in India, a large amount of money is spent on defense and space and aerospace sectors, because that is what is going to keep the country safe. So everybody works on security. So our materials research also predominantly focuses on security aspects, not only in India, but even in other countries. Most of the countries which invest a lot of money on research, they focus on security. Another important aspect where materials research becomes very important is environment. This is simply because you know that if you want to take, buy 1 liter of petrol now, there was a time when we were paying only 40 rupees per liter, but you know what is the cost of petrol right now. So that means anything that is fossil fuel based energy, which we are heavily dependent on, this is not a sustainable option. We are heavily dependent on gasoline which comes from other countries. So unless we look at green energy concepts and become self-reliant, it becomes very difficult. So therefore, worldwide, everybody is interested in developing green energy based concepts. So the entire economy is moving towards hydrogen based economy. Another aspect of environment is air and water. So let me just consider water, because water is one of the precious aspects. And particularly for somebody who lives in Chennai, we know the importance of water. So, and particularly freshwater crisis, I think Bangalore also, there are articles where Bangalore might be in deep trouble after a few years, as far as freshwater is concerned. So therefore, it's very, very important to conserve water, and whatever water bodies are there, one has to make sure that they are not contaminated, and even if they are contaminated, how to remediate them. So therefore, we are everybody's research, or many of them who works on topics, materials research, try to focus on these problems. The other problem, which is also something which is relevant in materials research, is food and health. And because everybody wants food and everybody wants health. But food and health is something that we are not going to talk about today, but this is still something that comes under the broad domain of challenges in materials research. But I will skip the food and health part, but security and environment is certainly those topics which are extremely relevant for most of the engineers at least. So the right part is mostly materials chemistry and engineering. The left part is mostly biotechnology, medical, but nowadays a lot of materials research also is focused on that part.
Sir, respected sir.
Yeah.
Sir, please, slide is not moving, sir.
Can you see the slide now? What slide are you seeing?
Sir, only first slide is there, sir. First slide we are seeing. Now it is moving, sir. Yes, sir. Yes, sir. Now it is moving.
Can you see right now?
Yes, sir. It is moving. It is seeing, sir. Yes, sir. Ceramic technologies for futuristic mobility, you see.
Yeah. So now I was showing you a slide on challenges in materials research. Can you see the challenges in materials research now?
No, sir, it's not coming.
I don't know why it is not coming, because
Can you close it and once again you can start, sir?
I will do that. Yeah.
Yeah.
I will do that. Just a minute. I will reopen the slides once again.
Okay, sir.
Are you able to see the slides now?
Yes, sir. It's visible, sir. You can press Alt F5, it will become full screen.
Alt what? No, I'm already in full screen, but I don't know. It might be a Google related.
F5, if you press, it will become full screen.
No, I'm using a Mac. I'm not using a Windows based thing. So I don't have those keys here. I am already on full screen.
Slideshow, sir. Slideshow, you can press.
I am actually on slideshow only, but I don't know why you are not able to see in slideshow mode.
Okay, no problem, sir. You can continue.
Yeah, but are you able to see the slides clear enough?
Sir. Now we are in laboratory for high performance ceramic.
Yeah, this is what I was explaining in the previous slide. Now, can you see the next slide on ceramic technologies for futuristic mobility?
No, sir.
Yeah, because I moved to the next slide already. Ceramic technologies for futuristic mobility.
No, it's not moving, sir. It's stuck there only.
Okay, I don't know now what is the issue, because I'm using my institute internet, so there should not be internet problems at least.
Now it has moved. Now it has moved. Yeah, now it has come. Ceramic technologies for futuristic mobility. Yeah, now it's moving.
Okay, now it is moving. So then I will keep it like this. Is it clear enough for you to see?
Yes, sir. Yes, sir. Yes.
Sir, please make it in the PPT mode, sir.
I made it in PPT mode, but then I was told that it is not moving further.
Okay, continue, sir.
For example, I have now gone to the next slide, challenges in materials research. Can you see the challenges in materials research slide?
No, sir.
Yeah, that's what. When I'm putting in PPT mode, it is not appearing for you in the. Now, can you see?
Yes, sir.
Yeah.
Yes, sir. Yes.
So this could be some kind of a compatibility issue with Google, possibly, because when I go to presentation mode, it is not showing. It is not moving. The slides are not moving.
Okay, sir. You can continue.
So if this is if you are able to see this properly, then I will go ahead. Otherwise, we will waste time.
Yes, sir. Please continue, sir.
Please continue.
Yeah. So I did talk about challenges in materials research, and I was telling you that security and environment are two topics which all material scientists would work on. Now I have moved to the next slide. So confirm that you are able to see, so that you are able to see materials.
Yes, sir. Yes, sir. Materials for extreme environment.
Okay, so I think I will go ahead with this mode, because if I go to slideshow mode, it doesn't seem to be moving.
It's okay, sir. Please continue, sir.
Yeah, I will continue. Otherwise, we are going to waste time. So we are looking at various extreme environments where materials research becomes important. For example, if you take a ship which is docked in its yard immediately gets fouled. You need some coating solutions to prevent fouling. Or if you take submarines which are underwater, which operate underwater, are subjected to high hydrostatic pressures. If you take space vehicles are subjected to extreme temperatures. Nuclear explosions, of course, nuclear explosions are not common, but certainly if there's a nuclear explosion, there are very different kind of situations that one has to deal with. Materials development becomes an important aspect. Last but not the least, electronics. I'm not going to talk about this electronics part, but heat generation electronics is a very important aspect. And again, ceramic technologies play a very important role. In fact, I still remember when we used to work on certain laptops 15 years back, the laptops used to shut down simply because of the heat. When there is extreme heat, the laptops used to shut down. So in my today's talk, let me focus on certain ceramic technologies and components which are very much relevant for us. But at the same time, I will also highlight how we, as a country, we are still finding it difficult to develop certain technologies. So I will highlight certain technologies where we are still lacking, and possibly that will lead to some people looking at certain areas where people should focus on in this country. So let me show you. Say, if you look at this slide, what you are seeing here, these slides show you some of the ceramic components which possibly many of you may not have seen. For example, what you see here is a gas exhaust valve made up of zirconium dioxide. Okay, zirconia. And on the other left-hand side, there are some ceramic-based rings and bearings which are replacing plastics for extreme conditions. On the right-hand side, some ceramic rotors made up of silicon nitride were actually fabricated at some point of time. Of course, not everything has gone into the market. Some of them stayed back at the laboratory scale. Some of them actually went to the production scale and are used in the industry. Let me just tell you one example, which is a very nice example, which I show it to many people. This is one example which is called chip-on-heat-sink technology. This chip-on-heat-sink technology is a technology which is again used in electronics, where the chips are built on heat sink directly. Now, when you have these electronic chips which produce heat, you need that heat to be removed out of these electronics, and therefore you require a heat sink. And people have been fabricating this chip-on heat sink technology. For example, this is from a company called Ceramtech in Germany, and this heat sink is basically something which can remove the heat that is generated. Of course, the immediate example that comes to anybody's mind is maybe copper or copper-based composites for extracting heat, but copper may not be always the best solution. So here, ceramics are concerned and are considered for heat sink technology solutions. And alumina or aluminum nitride is one of the standard examples that people have been working on, simply because of its thermal conductivity. Aluminum nitride certainly has a higher thermal conductivity than alumina. And if you look at the microstructure, this is what it looks like. Alumina microstructure and aluminum nitride microstructures are shown here. 100% dense aluminum nitride would be a very good example for a heat sink material. But imagine this whole technology is one single technology where you have an integrated chip on an aluminum nitride heat sink. And this is not something that is easy to make. India is not able to make. So I am just telling you some of the examples where industries are able to fabricate in other countries, but we are not able to make, because it's important to understand some of the technologies that we have to develop on an urgent scale. I'll show you one more example where some of the bearing rollers that are made up of silicon nitride. I think most of you are mechanical engineers, and you might have seen bearings. And most of the bearings that you might have seen are steel bearings with a steel ball. But we are talking about bearing rollers made up of silicon nitride. And these kind of bearings are important because silicon nitride is a very tough material with a fracture toughness of more than 20 MPa root meter. So although it is a ceramic, it is having very high fracture toughness. Most importantly, it is corrosion resistant. So if you can, and they are light. So compared to a steel bearing, a silicon nitride bearing made up of silicon nitride rollers, they are extremely useful under very harsh conditions, and where you require weight reduction, and at the same time where corrosion becomes a very important aspect, silicon nitride bearings can be very important. And you can see that it is already being used. In fact, recently we were talking with one of the companies in Chennai, and they were exploring possibilities of using silicon nitride based bearings. I'll show you one more example, which is again a technology that India is still not able to make, and people are trying to make in India, but we are not still at a scale where we can fabricate and manufacture and produce. What is this technology? We are talking of transparent ceramics. So you can see here, as you can see in the picture, this is a transparent ceramic. So it's not a glass. It is not a glass. It's not a window glass. Window glass will melt. If you go to temperatures beyond 400, 500, it would have melted already. But these are transparent ceramics based on aluminum oxide, or it could be even magnesium aluminum based oxide, where these transparent ceramics can be used for harsh applications. For example, this is an inspection window made up of this Perlucor is the trade name of the institute. The institute which first fabricated is the Fraunhofer Institute in Dresden in Germany, and they have named this transparent ceramic with a trade name called Perlucor. So this is a very niche technology. Not many people can still make it. Even Americans are struggling to make this, but it's an extremely important technology to develop, because this can have far-reaching applications, not just harsh applications, but also for defense applications, because you can always have very tough transparent ceramics incorporated in certain battle tanks. So it's a technology. In fact, I would say it's a technology that that only few countries, and I would say possibly Germany, has mastered, and not many other countries are able to do. Let me start with our actual topic today. So I just gave you a few examples of certain technologies in ceramics, which I think at least India should focus on, where some of the countries have already developed those technologies, but we are lacking behind and we have to focus on them. Let me start talking about challenges in the aerospace industry, because India has a very strong aerospace program, but particularly I would say space program. Most of you are aware of ISRO. ISRO has been doing a great job. And so let me take the example of the space industry. And I'm taking the example of a rocket. This is a PSLV rocket. I myself worked for ISRO Satellite Center long back, and I had some strong connection with ISRO long back. So let me start taking the example of a rocket. A rocket has several stages here. If you look at this, there are 4 or 5 stages, and a lot of parts go into it, metallic and non-metallic parts go into it. And some of them are subjected to extremely high temperatures. Some of them are subjected to extremely low temperatures. So you need materials which can be, you need different classes of materials which can withstand both kinds of temperatures, both extremely high temperatures as well as extremely low temperatures. So therefore, materials in the aerospace industry is a huge challenge. I will start with an example of a jet engine. Because why did I take the example of a jet engine? Because India is still not a manufacturer of a jet engine for aerospace application. People from Bangalore know that there is a GTRE, that is called Gas Turbine Research Establishment. Of course, they have been trying to develop the Kaveri engine. It has taken quite a long time. But technology of making jet engines is not very easy. In fact, India has struggled a lot in making, although space program in India has been very good because the propulsion technology has been mastered by Indians. But I think the jet engine technology, which is required, which is the heart of any aeroplane, when you actually fly, for example, from Chennai to Bangalore or Bangalore to Delhi or Bangalore to Frankfurt, you need a jet engine, a powerful jet engine. And we, in the country, we are still unable to make. And there are already private companies in other countries, Western nations, where they are able to make. For example, General Electric, an American company, can actually make a jet engine. Pratt & Whitney can make a jet engine. Rolls-Royce of Britain can make a jet engine. So there are private players in other Western nations which are already making state-of-the-art jet engines which can be fitted onto an airplane. We are not in that state. So hence, India as a country which is as large as India should certainly focus on developing certain technology where we seriously lack, and jet engine is a standard example that I wanted to take. Now, why jet engine is an important technology? Not just because it's we are not able to make. The problem here, as far as materials research is concerned, is it is extremely difficult to develop even materials for jet engines. So that is where we are even lacking. You look at this this example. Since some of you, or at least most of you, might be mechanical engineers, you will be able to understand this plot. This is a plot of relative cruise specific fuel consumption on the y-axis, and then you will see how the overall pressure ratio and maximum temperature range has changed over a period of time. And you can see from 1970s to around 2000, people are able to increase the operating temperatures to as high as 2000 degrees Celsius or in that temperature range. And that has not been very easy. In fact, it has taken a lot of time to achieve such kind of temperatures in jet engines. Now, to understand the complications of jet engine and what are the challenges, I have to show you a jet engine. This is an old jet engine produced by GE. Okay, I hope you can see the picture very clearly. And some of you might already explain in a classroom about its typical gas turbine concept. So you have a compressor, you have a combustor, you have a high pressure turbine, you have a low pressure turbine. The air fuel mixture gets compressed here, and the high pressure gases do get combusted, and these after combustion, the combusted gases drive the turbine. So that is where we are looking at. So obviously the high pressure turbine faces the high temperature. Now, if you want higher thrust in the jet engine to be achieved, then higher operating temperature must be realized. Unless you achieve higher operating temperatures, you cannot achieve higher thrust. But what is the problem? Higher operating temperatures are easy to achieve, but the materials should be able to withstand. That is a challenge. And to achieve higher efficiency, engine must be made significantly light without loss of thrust. And you cannot simply bring a heavy metallic metal which can withstand very high temperatures and do it, because you need a lighter material. So that is where the complications come. And while combustion is easy, the combustion gases where the temperatures are high, and it's important to develop materials which can withstand those temperatures. So that is the challenge. Now, what is the state of the art right now? Right now, people use nickel-based superalloys. So 70% of the weight of a jet turbine is made up of nickel-based superalloys. If you take a gas turbine, even today, the heart of the gas turbine is made up of, most of the rotating parts are all made up of nickel-based superalloys. Now, what is the issue? The nickel-based superalloys melt at 1250 degrees Celsius. Now, they are supposed to be operating at 85% of their melting point. That means you cannot go beyond 1000 degrees. Because if you go beyond 1000 degrees, then the nickel-based superalloy starts melting slowly. So you cannot do it. So there's a temperature limit. But if at all, if you are able to go to 1300 and 1400 degrees Celsius, then you can achieve higher thrust. So unfortunately, that is not able to be done if you want to use nickel-based superalloys directly. Also, please remember, these are rotating blades. When they are rotating at very high speeds, they are subjected to a centrifugal stress of around 140 to 150 megapascals. So that means the material is also creeping, because the materials are subjected to high temperature coupled with loads. So they are supposed to creep. So you need materials which are creep resistant. So that is where the challenge comes. So people, of course, have been looking at various materials that can be used for such applications. They should have very high, you have a lot of combination of several properties that people look for: high temperature stability, chemical stability, good creep properties, and so on. But it is very difficult. You cannot get all properties in the same material. So people have looked at various material possibilities. People have looked at refractory metals. People have looked at monolithic ceramics, intermetallic compounds, ceramic compounds, ceramic composites, and so on. Of course, there is no one single solution. One may have to adopt multiple solutions to solve these problems. But to even understand this problem, let me just show you the basic metallurgy of nickel-based superalloys. Of course, some of you might know the basic metallurgy of nickel-based superalloys. What is the basic metallurgy of nickel-based superalloys? A basic metallurgy of nickel-based superalloys is all about the gamma prime precipitates, which is in coherency with the gamma, that is nickel-rich matrix. And of course, you can see the electron micrograph here. So the cuboidal precipitates are basically the nickel aluminide precipitates, which provide the strength. And you have more than 10 to 15 elements. It's a concoction of several elements, because you add several elements for various purposes. You provide strengthening, you provide oxidation resistance, and so on. So you make these alloys. And of course, it has taken 100 years to have the technology developed. In fact, many people may not know that it has taken 100 years for not only developing nickel-based superalloys, but also even the casting technology. People initially had polycrystalline materials for their blades, which eventually now has moved to single crystal blades. So moving to a single crystal, making single crystal itself is a technology. And now in modern times, people use single crystal blades, because when you have single crystals, the creep resistance is increased to a large extent because you do not have any grain boundaries. And to understand this, it has taken people 80 to 100 years. But then, as I have already told you, nickel-based superalloy blades melt at 1250 degrees Celsius. But we want to achieve much higher temperatures in the engine, and we cannot use it directly. Can you use these nickel-based superalloy blades directly? No, you cannot use. Because if you use them, of course, then you will have to restrict the temperature to less than 1000 degrees. So what people do, people provide ceramic coatings. So people provide ceramic coatings onto these nickel-based superalloy blades. So that is where ceramics become very important for us. So, so we are looking at such developing ceramic coatings for high temperature applications. And you can see, for example, from 1940 to around 2000, people have now, I was just telling you that people were initially using wrought alloys, then people were using polycrystalline equiaxed cast alloys, then people were using directionally solidified nickel-based superalloys, and now people use single crystal alloys. SX means single crystal. And now people also at some point of time started providing cooling channels. Then now they also use EB-PVD TBC coatings. What is EB-PVD? Electron beam physically vapor deposited thermal barrier coatings. That's what EB-PVD TBC coatings mean. So with cooling channels plus EB-PVD TBC coatings, people are able to achieve much higher temperatures. And for example, there is a silicon nitride turbine also which has been kept here. But is still not being used, but still people, what is currently being used in jet engines are single crystal superalloy blades with thermal barrier coatings with cooling channels. That's what is the latest, what people are currently using in any gas turbine. And this is not very easy. In fact, remember, if the gas turbine fails, then the aeroplane fails, and it is loss of life. Directly, lives of people are involved. So you have to make sure that there is a very strong reliability in all this. And people have worked on it, and now more or less the technology is mastered by some of the aerospace companies which manufacture these components. Of course, there are several important requirements for coatings. I don't want to go into details, but this is called thermal barrier coating system. So this thermal barrier coating system is what actually enables the gas turbine blades to operate at 1200 to 1300 degrees Celsius, because these thermal barrier coatings is ceramic based, and therefore it is possible that they can operate not only at higher temperatures but also can withstand other issues like erosion and exposure to steam and so on. So that's what is being used. And for example, if you are from Hyderabad, you should visit ARCI in Hyderabad. So they have an electron beam physical vapor deposition setup. You can see how they actually deposit these materials. So what is this? How does this coating look like? So on the left hand side, you can actually see the blade, okay, the photograph of the blade, which is coated. Now, this is a blade of nickel-based superalloy, which is a single crystal, which is coated. Now, if you take a small portion of it and look at the schematic of what actually it contains, so this is what it is. So you have a blade, which is made up of nickel-based superalloy. Then they make a bond coat over that. So they use a bond coat. Then over the bond coat, they make a top coat made up of zirconia. And then, of course, here the combustion gases are coming from the right-hand side. Okay, this same schematic is shown here. So you have a superalloy blade. Over the superalloy blade, you have a bond coat. Okay, a bond coat is of around 100 micron thick. And then over that, they deposit a thermal barrier coating. And this TGO is called thermally grown oxide, which is typically alumina that grows with time. And this is a very interesting concept. People have not randomly selected these compositions. There are reasons to select these compositions. I will show you in the next slide why they have selected these materials. So if you look at this, the compositions, of course, the substrate is a nickel-based superalloy. The bond coat is typically made up of some metallic material like nickel, chromium, aluminum, yttrium, and so on, which is around 75 to 100 micron thick. A thermally grown oxide will grow with time. And as I said, the ceramic top coat is a yttria stabilized zirconia. Okay. So, and I will show you now in the next slide why this material combination. This material combination has been chosen because there are two important aspects that needs to be considered. That is thermal conductivity and thermal expansion coefficient. Remember, these components are subjected to high temperatures and they also cool down. Let us say they are flying. You are flying in the aircraft. So they are operating at high temperatures. And when you reach your destination, the turbine is switched off. That means they are again getting cooled. And again, they are going to switch on the turbine when the flight is going to take off. So they are subjected to thermal cycles. When they're subjected to thermal cycles, it's important to have different material systems which are there together should have more or less similar thermal expansion coefficients. If you look at the expansion coefficient of zirconia, the thermally grown oxide alumina, and the nickel-based superalloys, they all have a more or less same expansion coefficient of around 10 into 10 power minus 6 per degree Celsius. And if you look at the thermal conductivity, we require low thermal conductivity for the ceramic coating because we do not want the substrate to be exposed to high temperatures. So therefore, you can see that the thermal conductivity of zirconia is around, say, around 2 watt per meter Kelvin at 2000 degrees Celsius. It's extremely good because it's going to prevent the substrate from being exposed to very high temperatures. And not only that, zirconia has very high hardness, it has high melting point and protects the substrate to a large extent. So that is how people have selected zirconia as a top coat. And that is why if you look at the last 20-25 years, a lot of people have worked on the use of zirconia as a thermal barrier coating system. In fact, in some 10 years back, people were also looking at providing yttrium stabilized zirconia coating for even automotive components. Okay, even for automotive components. Now, this is the methodology, coating methodology that is used. I said the electron beam physical vapor deposition, that is EBPVD. So this is the most likely technology that is used for providing top coat on such substrates. If you go to AICTE Hyderabad, AICTE Hyderabad has an electron beam physical vapor deposition setup. You can have a look at it. I think if you go at the right time, you may also have the possibility to see them coating substrates using EBPVD. Plasma spraying process is a relatively cheaper process. Many of the companies might already have a plasma spraying process. So this is easier to make and this is easily accessible. And you can make plasma spray coated coatings also. But the only thing is that the kind of microstructures that you develop will be different. Usually plasma sprayed coatings are used for non-rotating components. Like static components, you can use them. For rotating components, electron physical vapor deposition would be the best thing to do. But plasma spraying process is easily accessible. At least I know in Bangalore where they make ceramic coatings using plasma spray process. For some of the static components, it can be used. I am just showing you the microstructures. We are material scientists and we correlate every property with the microstructures. You can see that the microstructures are very much different if you use plasma spraying and electron beam physical vapor deposition technique. If you look at the electron beam physical vapor deposition technique, the microstructure, if you see, the top coat is with columnar grains, and there are intercolumnar gaps, which actually helps because it will help in strain compliance. So it will help in not easily cracking. If you take plasma spraying process, it creates in these splats and porosity between splats. So this may not be the best thing for rotating components because if you have plasma spraying methodology for rotating components, it gets peeled off. It may be okay for static components. So it's very important to look at the microstructure and coating methodology will determine the microstructure and microstructure will determine the properties of the material. Of course, there are failure mechanisms. They do end up with interfacial strain, which gets accumulated over a period of time. So you need to design this properly. For example, we have to ensure at least 1,000 hours of operation or 1,500 hours of operation of gas turbine without any failure. That is important. Remember that irrespective of whatever design we make, the interfaces will always have some strain. And this strain gets accumulated with time. And any strain accumulation with time leads to rumpling and eventually failure at the interface. That is imaginable because we are talking of a ceramic coating on a metallic substrate. So even though we try to match the coefficient of thermal expansion, there will be always some mismatch strain that gets accumulated when the component undergoes its thermal cycles. So we should be aware of that and we should know when it will fail. At least design engineers should have competence to find out how much time you have before it fails, because nothing is perfect. You must know that everything has to fail at some point of time. All that we do is that we make it sure that it functions for a given amount of time. That is very important. We should not face a sudden premature failure leading us to shocks. Okay, that is what we as design engineers do. Design engineers do not design components for eternity. Design engineers plan with a certain shelf life. Everything will have a shelf life. You plan for that shelf life and you design for that shelf life. So that is what we need to keep in mind. So that is as far as the applications in the aerospace sector is concerned, particularly the turbine blades. Let me just take you through some of the other components that are made up of ceramic materials and composites. And again, where I feel that India has made some progress and where India still has to make some progress. I'm showing you one picture here. I hope you are able to see. This is a picture of silicon carbide fibers. They are called nickel-on fibers. And high purity silicon carbide fibers are called high nickel-on fibers. It was first processed by a Japanese scientist called Yajima. And therefore, the process of making the silicon carbide fiber is called Yajima's process. Now, if you ask me, why did I show you a silicon carbide fiber picture here? It's simply because this was first processed in sometime in 1970s in Japan. Now it is 2021, end of 2021. India is still not able to make silicon carbide fiber, even to this date. Even to this date, India is not able to make silicon carbide fibers. Now, if you ask me, why do I have to make silicon carbide fiber? We need to make silicon carbide fibers because silicon carbide fiber becomes reinforcement for ceramic matrix. And such silicon carbide reinforced ceramic matrix composites can be used for high temperature applications, which is very much relevant for the aerospace program. Right now, India is not able to make. What India is able to use right now is carbon fiber reinforced ceramic matrix. For example, carbon fiber reinforced silicon carbide matrix composite is currently being used. For example, if you go to Vikram Sarabhai Space Center in Thiruvananthapuram, if you get access to go there, they are able to make carbon fiber reinforced silicon carbide matrix composite. But what is the problem? The problem is that it cannot be used for extremely high performance applications. There is a temperature limit because carbon fibers cannot be used beyond a certain temperature. So therefore, we are still limited by our inability to make silicon carbide fibers. In fact, last year, or just before last year, when the Prime Minister's Ministry of Defense had organized a program regarding Make in India and Atmanirbhar Bharat program and to find out what technologies India should focus on, I was leading the ceramic technologies program, and we had a summit for about 3 days, inviting all the best experts in India and outside the country. And we identified this aspect, that one of the important aspect that India should focus on is silicon carbide fiber. In fact, when I presented this to the committee, the high-powered committee, which was also consisting of the Planning Commission and the Chief Scientific Secretary to the Prime Minister and so on. In fact, I did mention to them that India has to certainly immediately focus on silicon carbide fiber production and develop this technology, because it not only helps us in making us self-reliant in the aerospace sector, but silicon carbide fibers right now you cannot even import. In fact, there is an embargo. Japan makes it but doesn't actually give it to India. In fact, Germany makes it now, France makes it now, they don't give it to India. So there's an embargo. We cannot make it. And at the same time, they're extremely expensive. So if you develop the technology of making silicon carbide fibers, and if a private company even gets the technology, they can make huge money. In fact, we are talking of tens and thousands of euros of what the technology this is. So therefore, it's very, very important to understand this part. I will not go into the how ceramic composites are made. I think this is a basic concept of any composite, whether it's a metal matrix composite or a ceramic matrix composite. We typically have a reinforcement and a matrix. But what is more important are the fiber reinforced composites. These are the only ones which actually can be used for practical applications. Rest of the composites are nice because they do not, they are fine. They may have some marginal strength improvement and so on. But for most of the, at least for ceramic matrix composites, which are meant for aerospace applications, the only possibility which is viable and which is dependable is fiber reinforced composites. And such silicon carbide matrix composites are already used for advanced jet engines by some of the aerospace companies. Of course, people cannot use silicon carbide directly because silicon carbide fracture toughness is only 2 to 3 ampere root meter, and it simply cracks into pieces. We cannot use silicon carbide directly, obviously, and make jet engines out of it. So obviously, one of the ways to use silicon carbide is only through ceramic matrix composite, and I'll show you what it is. People are right now, people who makes these composite use silicon carbide matrix. So the matrix is silicon carbide, and they reinforce it with silicon carbide fiber. You can see that this is a scanning electron micrograph of silicon carbide fiber reinforcement with a matrix surrounded. And they also designed the matrix to have a healing capability. It's a multi-layered healing, self-healing matrix. So even if there's a crack, the matrix should heal under the influence of temperature when it is operating at high temperatures. So it's a very niche technology where you develop the material system in such a way that even if there's a crack, the crack should get healed in the matrix. At the same time, they provide some kind of an interface between the fiber and matrix. They use pyrolytic carbon. So that means every silicon carbide fiber is coated with a pyrolytic carbon. And this pyrolytic carbon acts like a fuse. So whenever there's a crack, it deflects the crack. So when you use ceramic matrix composites, it's all about how to prevent cracks from propagating further. That's very, very important because you are dealing with ceramics. Hence, for us, it is very, very important to make sure that cracks, even if they are introduced, they do not propagate. Okay, so that is very, very important. And now people have learned and people have understood this technology very well. I'll show you in the next slide why actually silicon carbide fibers are important. Now, if you look at this material design aspect, now silicon carbide fibers have a little bit higher density, but oxidation starts only beyond 800 degrees Celsius. And the silica scale that's going to form over that can be stable till 1500 degrees Celsius. And silicon carbide also has a high tensile strength and modulus. So that is why it is important for us to make silicon carbide fibers, and that is why it's important for us to reinforce silicon carbide fibers in a silicon carbide matrix. I hope I have convinced you that how important it is. Right now in India, if you take the space program, they are using only carbon fiber, and carbon fiber already starts to oxidize around 400 degrees Celsius. Not useful, and the strength and modulus also is seriously compromised. And of course, you need an interface between fiber woven fabric and as well as the matrix. So people typically go for a pyrolytic carbon or hexagonal boron nitride, which will not only help in adhesion but also help in crack deflection. Of course, your matrix should be self-healing, creep resistant, and refractory. And what is the best matrix that people think of? Silicon carbide matrix. How do you make silicon carbide matrix? People use infiltration technology. Again, if you have access to, say, go to Vikram Sarabhai Space Center, you can see the chemical vapor infiltration technique. So basically, you use a precursor which can convert where you can, the precursor which eventually can transform to silicon carbide. So they use such precursors, transform, infiltrate it through vapor phase, and then heat treat to convert to silicon carbide matrix. So that's it. Again, people have learned to make it. Making silicon carbide matrix is something that India can already do. We have CVI furnaces that can be done. So right now, the only hiccup right now, the only problem that India is right now facing is making silicon carbide fibers. If we do that, I think we have achieved some kind of self-reliancy and self-sufficiency. I'll show you one example right now where such silicon carbide composites are used for jet engine applications. This is from a French company. The results that I'm showing you is from a French aerospace company called SNECMA. So SNECMA is a French aerospace company. I told you there are a few aerospace companies. Most of them are private companies, by the way, which make these jet engines. I told you about Rolls-Royce. I told you about GE. I told you about Pratt & Whitney. And SNECMA is a French company, which makes, again, jet engines. And you can see that their jet engines with self-healing matrices can be operating at 1000 degrees and for several hours. So they They try to test, and they have tried to test some of their next generation, silicon carbide matrix composites, and with a self-healing matrix, which can operate at 1000 degrees or even more than 1000 degrees without any deterioration for thousands of hours of operation. So this is something that they have already achieved, and this is what we need to achieve as well. Okay. So I will show you a video of how this is made later. Let me finish off the presentation first. So, and then I will show you the slides. I will show you the presentation, on a video presentation on how it is made. So we, in our lab, we do this. In fact, we in our lab, we produce these precursors for making certain ceramic compounds, and we use different ways to make these ceramic materials. Like vapor technology, we don't do much, but liquid deposition we do, and solid state pyrolysis we do to make ceramic materials. And we actually can make a variety of things. In fact, we can coat them. We can make. We have already started to make small fibers. In fact, we are now currently interacting with the government and defense labs to see if we can get funded for making such ceramic fibers. We are already doing it, and we are already working with Vikram Sarabhai Space Center to provide ceramic coatings on some of their components which are used for high temperature applications. We are already making some ceramic fibers, as I said. We are making porous materials and so on. We are already making some of them. And because we use, see, this is not, see, for many of them, when they talk about ceramics, they think it is powder metallurgy route. That is taking ceramic powders and sintering them. We don't do that. We are not using powder metallurgy route. What we use is a precursor. That is a polymeric precursor, which has the final composition of the ceramic in its backbone, which can be converted into a ceramic at a higher temperature. So that gives a lot of flexibility in terms of not only chemical composition, but also flexibility in making parts. For example, you can see this is some kind of a silicon carbonitride micro gear, which we have done by injection molding. This is a silicon carbonitride atomizer. So you can actually cast parts, because we are dealing with pre-ceramic polymers, which can be molded and which can be eventually converted into a ceramic. So therefore, it is possible to adopt all the polymer processing technologies and actually get the near net shaped ceramic component. So that is what gives us a lot of flexibility when we work on precursor route of making these materials. In fact, in the country, I think our group is one of the pioneering groups which uses precursor or pre-ceramic technology to make ceramic components. You can look at our website and you can look at our publications. You can see what we have been working on, and our lab is one of the pioneering groups. Again, as I said, we are now making oxide and non-oxide fibers. In fact, we are now patenting all of them, because we know this is one thing which I always wanted to say. India never bothered about patenting. It's very, very important to patent. In the academic world, when you develop things, it's important to protect knowledge. And India historically has not focused on patenting the technology that you develop. So I also urge the academicians who are here that when you develop any kind of technology, when you develop any kind of knowledge, please ensure that that knowledge is protected, that knowledge is patented. That's very important, and we are doing that. Everything that we developed in the lab right now, we apply for a patent. We first file an Indian patent, and then if we have sufficient money, we interact with industries and see if we can file patent in other countries. So anything that we develop, including material development, in fact, even if we develop a new material, we are patenting it. And IIT Madras during the last 5 years has invested a lot of efforts in helping faculty members to patent. I also urge, for example, in your institution, if you do not have a special IP cell, intellectual property cell, I urge you to create an IP cell and help faculty members to protect knowledge and protect technology, and have the technology registered in your name and or registered in your institution's name, because that is very important. Otherwise, you are going to lose your knowledge to somebody else, and if somebody else makes it, that person will be able to produce it as well. And this is to show you how ceramic coatings can be provided onto some composites. And if you coat it, you can actually see that it can be used for an extended period of time. This is tested at 1400 degrees Celsius without any weight loss. So we can make in our lab ceramic foams. In fact, our idea of making ceramic foams for two purposes. We were looking at ceramic foams for military applications, for energy absorption. and we were interacting with some defense industries for that. We were also developing ceramic foams for water treatment, because you need very high surface area. And so we are looking at ceramic foams for both structural applications and functional applications. So of course, you need to make sure whether if you are looking at structural applications, it should, and at high temperatures, you must certainly look at its damage resistance and so on. That should be doable. So in our lab, since we work on the so-called PDCs means precursor derived ceramics. Our lab is very well known in making these precursor derived ceramics. In our lab, we are very well known for that, and we develop a lot of silicon-based polymers. And in fact, some of the pre-ceramic polymers that we are developing, we are now patenting it, possibly in a week's time, which are meant for defense applications. In fact, when I was visiting University of Bayreuth in Germany last year, they were already making CMC brakes. In fact, in some of the motor vehicles, they are already both like Mercedes-Benz and so on, they're already using CMC-based brakes. And of course, I may not have time to show the pictures which I have taken. I can show that privately later if somebody wants to see. And they use these to make sensors. And so there are so many possibilities of making these materials for various applications. In recent times, we are working with the Army. I will show you a brief, I'll spend maybe 5 minutes on how ceramic and ceramic-based components are useful for the military. And I urge people to look at those applications as well, because not many people look at military applications, but you have to look at that because there is enough and sufficient scope for use of ceramic matrix composite in the military and for defense applications. So people in America have already started using ceramic matrix components for military vehicles. Ceramic matrix composites may not be extensively used in civilian aircrafts, but certainly it is already extensively used for military aircrafts, because military aircrafts, military vehicles, the number of people involved are minimal and so on. So therefore, you could take that risk. And people have already started using hafnium oxide-based materials, for example, which had withstood 300 hours of test at 1650 degrees Celsius. It's already being used in America. I will show you one battle tanks. In fact, we were recently discussing with the Indian Army about this. Now, what is the problem with the Indian Army? Now, Indian Army uses battle tanks. And these battle tanks, some of them are procured from Russia. And of course, after they are procured from Russia, they are renamed. For example, the one which you see here, one is called Ajeya. Other one you see in the middle is called Bhishma. And beside that, there's Arjun battle tank, and you must have heard of Arjun battle tank. And you can see that most of these tanks are very, very heavy, close to 50 tons, 50 to 60 tons. And 50 to 60 tons, and we are talking about a cost of 70 crores, 50 to 60, 70 crores. Now, recently, when I was talking to the Army General, one of their senior Army commanders, we were having a discussion with them, and they said the biggest problem for them is these tanks are made up of rolled homogeneous steels. The problem with them is the density, very heavy, close to 8 grams per cc, and such heavy vehicles are difficult to maneuver, and particularly when you want to move very fast, if it is very heavy, you cannot move fast. And so there's a lot of inertia because of the weight. So they were looking at possibilities of getting the same kind of performance as you would get using a steel tank, steel armor. They wanted to use some other ceramic based armor. So they did not want steel armors, because steel armor, if they replace steel armor by a ceramic composite based armor, there would be a lot of weight saving. So they were looking at that possibility. So right now we are working with the Indian Army to see how to replace armor steel with ceramic composite armor, so that there is significant weight saving for the battle tank. In fact, I should tell you that China is far ahead. In fact, what I liked about China is that they are able to proceed much, much faster than India, because on many fronts, I think China has already overtaken India. And if you look at one of the lightest tank in the world, you may be surprised to know that the world's lightest tank is right now from China. In fact, they are able to make a tank which is around 33 to 35 tons, which is much lower than the other battle tanks which are around in the world, which are used in the world. And of course, what metal system they are using for their armor is not revealed. Obviously, it is not revealed. But there are, of course, hints that they may be using ceramic matrix composite based armors. And because already there are German companies which make such ceramic composites. But we don't know what exactly the Chinese have used, but certainly they have been able to reduce the tank weight by at least 20-30%. So India is also, but right now Indian tanks, Arjun tank is double the weight. So unless we reduce the weight of these tanks significantly enough, we will lose that competitive edge against the hostile neighbor. And of course, we were telling them that one of the possibilities is to use boron carbide ceramic armors. Of course, it's boron carbide armors are already known in public, but you don't use boron carbide armors directly. There are ways and means of making armors. And but that is one possibility, that using a boron carbide ceramic is one of the possibilities, because the density of boron carbide is around 1.5 gram per cc or so, which is very, very light. But of course, you don't use the boron carbide armor directly. You need a multi-functional, multi-layered ceramic armor. And that is again a technology that one has to develop that is being currently looked into. And therefore, that is where ceramics become play a very important role. And just to give you an example, it gives you a lot of weight saving, because you are looking at extremely low density materials. Hardness is very high, compression strengths are very high. So it is possible that we can use some of these ceramic based materials for some of the defense applications. So of course, the rest of the process of making boron carbide and all is known. In fact, there are even private players now, 1 or 2 companies, even in India, which you can contact them and make. If you give them the material, if you tell them how to make this, they already know to sinter and give you boron carbide plates. Of course, they can make you boron carbide plates like this, but how to make a complete armor from that is left to your design. Please remember that. So this is only one part of the story. To sinter a boron carbide based small block is one part of the story. That is possibly one of the important part of the story, but that's not sufficient. You still have to make an armor, complete armor. It could be a body armor, it could be an armor for the battle tank. So that is again a complete technology one has to look at. But there are at least one good thing is, at least there are some 2-3 private companies which can sinter and give it to you. They can make boron carbide plates and give it to you. So if you have ideas of how to use boron carbide plates to eventually make an armor, and if you can prove it that your technology is really the best, of course you have possibilities to interact with appropriate defense agencies for funding, and as well as for taking them from the lab to actual on-site. This is only to show you that there are different kinds of designs, and this is an example of showing you an armor for a soldier using boron carbide based armor, which will prevent any kind of penetration by bullets. Please remember, some of them can be used for nobody wants to use armors for single time use, because if a soldier is on the battlefield, it is not for one time use. The armor, a steel armor it's a plastic, the steel armor is deformable, so therefore it can be used multiple times, no problem. But ceramics, you have to be very careful, because if it fails and if it actually gets destroyed, then you will lose the advantage of wearing a light armor. So you need to therefore make an armor which can be used for multiple shots. So when you look at army's requirements, they say, okay, I need a light armor better than steel, but can it withstand multiple shots? So that's what army would ask. So your design should be such that it can withstand multiple shots. That's why I said making boron carbide pellet is easy. You approach this company in Gujarat, they will make you and give you a few pellets. But can it be used directly? No, because once a bullet hits it, it's going to break into pieces. So you need to build a comprehensive, complete armor. So that is where the challenge is still there. For example, I'm showing you how such a boron carbide armor is made. You can see several such hexagonal platelets of boron carbide sintered plates are actually assembled onto, it's a multi-layered, multifunctional thing. So it depends on, your ideas. For example, one of the popular ideas is having a nylon cover over boron carbide with a Kevlar backing. It's a popular thing. But again, it may not be the best idea, but at least something people have tried out is something that you must be aware of. I wanted to show, I have now talked about aerospace, have talked about use of ceramic based composites for military and defense. Let me end my talk with automotive applications. I don't know, how many of you have seen this photograph. This photograph is of Bosch. And I think most of you know Bosch, Robert Bosch. Robert Bosch was an engineer, mechanical engineer, by the way. And he was from Stuttgart. And when he started his career in life, many of you may not know that he started his career in the workshop. He had his own workshop for precision mechanics and electrical engineering. And then he was only 25 when he started this workshop. And now Bosch is a very big company. And if you go to Stuttgart, actually I lived in Stuttgart for 6 years. I have visited Stuttgart Bosch. It's one of the very prominent automotive companies. And many of you know Bosch. And I just wanted to show this to you because his technology on magneto-ignition device and high voltage spark plug, actually today, why Bosch became a very well-known company, because they developed technologies which were technologies which are used for the automotive companies. So that is why it's very, very important for you to focus on technology development. So that is the reason why I'm also repeatedly telling that it's important to focus on technology development, and technology development that will make the country strong, that will help you make money, and that will eventually help the economy grow. And I'll tell you one example in which some 10 years back, where they produced a ceramic glow plug. Many of you have heard of spark plug. So very similar to spark plug, in diesel engines, people use glow plug in Europe, because there's a cold start problem in Europe. And because these are cold countries, and many times diesel engines don't start, and they require a glow plug to help the engine start. And for that, they have produced a silicon oxycarbide based glow plug, which can heat up to 1300 degrees Celsius in less than 2 seconds. And that is something that people have tried to use. There was a press release in 2006 by Robert Bosch that they wanted to use such a silicon oxycarbide glow plug for diesel engines, which will solve the cold start problems. I mean, I'm just giving you some examples where ceramic-based materials have been explored in automotive industries. This is a ceramic turbocharger made up of silicon nitride. So people explored making turbochargers. Of course, if you know how turbochargers are made, turbochargers are not typically made up of silicon nitride. They are metallic materials. Typically, they make it using metallic materials. But people have tried to use, the Japanese have tried to make ceramic turbochargers made up of silicon nitrides. And they have seen that there is increased efficiency. It may not be very well seen in the market, but certainly attempts are being made to replace some of the turbochargers, metallic turbochargers, with ceramic turbochargers. That is already being explored. And this, what I'm showing you, is already there in the market. I think this has already been used in the industry. People are already using it. In fact, a few minutes back, I talked about ceramic brake disc using carbon fiber reinforced silicon carbide composite. And in fact, it's already being used in high-end Mercedes and BMW German cars. It's already being used. It's also used in some of the two-wheelers in Germany. High-end two-wheelers, certain brake discs are already made up of carbon fiber reinforced silicon carbide composites, simply because it's very, very light. And there are already ceramic components for gas purification, for exhaust. It's already being used. So this is already being used, and there is nothing new in it. If you're not aware, I think you should be already aware that it's already being used. So people have already tried. It's not very new. People have already tried to use ceramic-based components in engines, in automotive engines. Some of them may be available in high-end cars, maybe not in low-end cars, because to make these ceramic materials composites and use them, they are expensive. They will not be cheap. So you may find such ceramic-based components, in high-end cars or in high-end two-wheelers and so on. May not be in your usual two-wheelers and cars which you find on Indian roads. But it is already being tried. You can see that some of these were already tested on roads in Japan in the 80s. So it's already being used by people in other countries on high-end vehicles. I finally stopped with this because when we interacted with the planning commission and with some of the secretaries of various departments when we hosted the Vaibhav Summit, I had the opportunity to show this to the principal scientific advisor to the Prime Minister, and as well as some of them. We discussed with them openly as to what are these technologies, at least ceramic technologies, that we have to focus for a self-reliant and secure India. In that, we identified a few technologies and we even told them that this is very important to focus on, and what are the high priority strategic areas that we should focus on. And as I said, ceramic fiber technology, particularly silicon carbide fiber technology, is something that we have to certainly focus on a priority basis. And making such ceramic matrix composites using silicon carbide is certainly of interest and should be accelerated. And we certainly have to also focus on ceramic energy harvesters, because energy harvesting is very, very important. We are looking at energy technologies for the future. And energy technology, if you come to IIT Madras, Professor Raju did his PhD in IIT Madras. I'm not sure if during his times he had seen, if you now come, almost on every building, on top of every building, we have solar panels. So we cover, I don't know, maybe possibly 20 to 30% of our energy requirements through solar panels. The exact amount of energy saving possibly the Dean Planning can give, but I'm sure that we have been able to be less dependent on the Tamil Nadu Electricity Board, because we are now able to tap onto solar energy to a large extent. And energy harvesting is important. So that's very important. And other priority areas that we were also suggesting the Planning Commission and secretaries to various ministries on that day is that we should also have several testing centers, because we do not have testing. When we develop materials, we also need to test them. And to test them, you need nodal centers across India. India is a huge country, and we cannot have only one or two facilities. We have to have facilities where people can test their components or materials that they have developed. And we should also look at manufacturability, which is again a very big problem, because India has not focused much on manufacturing, on some of the niche technologies. So we also said how important is to develop manufacturing technologies and upscaling it. Last but not the least, we also said we have to enable indigenization and entrepreneurship. That means we have to enable, if you want Atmanirbhar Bharat or Make in India to happen successfully, encourage young engineers right at the end of their bachelor's degree to think about entrepreneurship, start their own company. In fact, gone are those days where you wait for a company to recruit you. It's important that you do think about, there are several ideas. In fact, there are so many areas where we are importing things. So for example, in fact, when we discuss with high profile people, both in India and abroad, we realize that getting high purity raw materials itself is a big problem. And we don't have any companies in India which can make high purity raw materials. We depend on at least some of us who work on ceramic research, we depend on Sigma Aldrich, Alpha EZ, all of them are foreign companies. We don't have Indian companies which provides us ultra high purity raw materials. So there are several avenues for indigenization and entrepreneurship. So we told all this to the high-powered committee which was there in front of us on that day. And of course, they did accept that, and they did say that this will be taken up. But due to pandemic last year, I think some of these things were kept on hold. But we are going to again pursue this with the ministries. Finally, I just wanted to tell that please do not mimic others. It's important to be original, because original thinking leads to breakthroughs. Many times we have a tendency to simply copy what others do, what Western countries do, because what Western countries do may not be useful for us. We have to develop technologies what are useful for us. Then, and if we are original in our thinking, that thinking can eventually translate to technology which can be patentable. So therefore, it's important to encourage original thinking, because original thinking leads to breakthroughs. So that's what I finally wanted to say. And that does not mean that you should not look at research of others. You certainly have to look at what others do and across the world. That's important to know what we are doing and what others are doing to compare ourselves and where we lack. It's important to do, but that does not mean that we have to copy them. I think this is where I want to stop. And I think I was asked to give a talk for 1.5 hours. I have finished 10 minutes earlier or 15 minutes earlier. I would like to thank you. Thanks to Anand, thanks to Raju, Professor Raju, for inviting me. And of course, thanks to Ambedkar Institute of Technology for asking me to give this talk. I'll be very happy to discuss the next 10-15 minutes if you have any questions. I have just provided some brief picture about the technology development, and particularly ceramic technology development, and how it is important and relevant for India, and where we lack also. I think that I have told, and I'm now open to any kind of discussion with you.
Should I ask a question?
Please.
Myself, Dr. Pankaj Kumar Singh from IIT BHU.
Yeah.
Your presentation was very nice.
Thank you, Professor Pankaj.
My question is very simple, as you are always using the ceramic every time.
Yeah.
I'm just asking that how ceramic is different from other branches of sciences or engineering group like the material science, metallurgical group, and the chemical engineering, chemistry. How it is different from those groups?
Okay, let me give you a little bit broad answer, and then I will come to specifics. Can you mute your mic because there is echo? Yeah, thank you. Thank you, Dr. Pankaj. See, one thing is the number of ceramic departments are very limited in the country. That is one thing. Very few. In fact, ITBHU has a ceramic engineering department, but not many engineering institutions have a ceramic department itself. In fact, the impetus that is given to ceramic departments is not at all there. That's the first problem. Let me tell you the problems and larger issue, and then I'll come to specifics. And even if there are ceramic departments, for example, Anna University across IIT Madras also has a ceramic department. And one of the complaints that I hear from students is lack of job opportunities. So lack of job opportunities is another thing which has actually limited people even to choose ceramic technology or ceramic science. So one thing that I would like to emphasize is what people study. People study based on the available opportunities. If opportunities are not there, people will not take up. If people don't take up, then how will we actually develop things? So it's a vicious cycle, and where we are into deep trouble, because if good students don't take up ceramic technologies, how are we going to, or if they don't study ceramic science, how are we going to develop ceramic technologies? So that is one kind of problem. Now, if you ask me why, how is it different? It is different in the sense that all of us work on, many of them work, I'm in a metallurgy department, 80%, 85% of them work on metallic materials, steel, for example, aluminum alloys, for example. But then they are not solution for all problems. That is the reason why I gave most of the examples that I was giving was aerospace. In aerospace, for some of the niche applications, you require ceramic technologies. In fact, if you want to use, if you want to operate it at 1500, 1600 and so on, there's no other option other than to go for ceramic matrix composites and so on. So therefore, you need solutions, ceramic technology solutions, particularly for structural applications where temperature becomes an important issue, where we are talking about 1500 degrees Celsius and above. Metallic components simply fail. You cannot think of metallic components. Okay. And not only structural applications, there are several functional applications where ceramic plays a very, very important role. For example, photocatalysts. Most of the photocatalysts that can be practically used are all based on ceramics. And many of the sensors, they're all ceramic based. So therefore, you find a lot of structural and functional applications only for ceramics. So therefore, this talk was, of course, my experience and expertise is in the area of ceramics and ceramic composites. And I gave you a few examples where they can be used. I don't know if I answered you. What?
No, sir. But my question is again.
Hello.
On that same place, that how it is different from the other groups.
What do you mean by what is the difference that you are talking of?
As it is using the chemical like the silicon carbide and other things you are saying. Chemistry is also using. Chemical engineering also using the same thing. Material science is also doing. How it is different?
I will let me tell you. The ceramic science, unlike many other disciplines, is very, very interdisciplinary, because ceramic science requires very strong knowledge in chemistry. So, and it also requires engineering approach. You can find people in chemistry department also working on ceramics, but they may not be able to produce structured ceramics for aerospace applications. Okay, so because you require engineering skills to also take things beyond laboratory. But certainly ceramic science and technology is a combination of chemistry, metals chemistry. It does involve chemical engineering, because there are people in chemical engineering who also works on ceramics. There are also people who work in mechanical engineering and metallurgy who also work on ceramics. It's a highly interdisciplinary field. For example, I'm a mechanical engineer basically by training. Subsequently, my master's is in metallurgy, my PhD is in material science. I use my knowledge in mechanical engineering and metallurgy both to develop ceramic related technologies for structural applications, because in my lab we heavily focused on structural applications for nearly 15 years.
Any questions from other participants? You can please ask.
Jay was about to ask some question. You can ask.
Hello, sir. Hello. Hello.
Yeah, you can answer. You can ask.
You can ask.
Sir, good afternoon, sir. Good afternoon, sir. Hello.
You're audible.
Hello.
You can ask question.
Audible,
Please
sir?
go ahead, Jitendra, I can hear you.
Yeah, sir. It's a nice presentation, sir. Thank you. Sir, I am working on metal matrix composites area. The question is, when we talk about ceramic matrix composites, I'm not in depth, but the thing is, when you're going for both the matrix and the reinforcement, both are ceramic case, the density matters a lot. It means the question is, if I take silicon nitride, it is somewhat more than the density of the aluminum oxide Al2O3. So how the question is how we can the challenging factor is with respect to synthesization, sir. What kind of casting techniques we need to adopt, and what are the parameters we have to consider, sir? Whether it is related to this particular talk or I don't know, sir, but I want to know from your end, sir.
Okay, I did not show you the processing of these. Unlike metal matrix composites, ceramic matrix composites, particularly which are used for applications, are not used. Do not follow the same methodology as you would use for metal matrix composites. One of the techniques that is used for making ceramic fiber reinforced ceramic matrix composites is, for example, you take the woven fabric of carbon fiber fabric or silicon carbide fabric, and you take those fabric and infiltrate it with a chemical precursor. That is, a precursor based matrix is infiltrated. So that is why I said chemical vapor infiltration technique is used in vapor form and then infiltrated thoroughly over several cycles, and then you heat treat it so that the vapor, the precursor or the pre-ceramic chemical is converted to ceramic after heat treatment. It's not that ceramic matrix is used and you deposit or you reinforce with ceramic fiber. That's not the way to do. You actually take the entire stack of ceramic woven fabrics and then infiltrate it with the pre-ceramic polymer or the liquid precursor, and then transform that liquid precursor into ceramic. So chemical vapor infiltration technique is one of the techniques that is used for making large size aerospace components of a certain shape, if you want to do it that way.
Thank you, sir. Thank you, sir.
Any more questions? If there are any questions, you can ask Professor over his mail. You can see his mail ID in the website of IIT Madras. Professor, thank you very much for giving such a wonderful talk. You covered all the areas right from aerospace, automobile, and research related to ceramics. I'm really glad that even in our institute, Ambedkar Institute of Technology, what you mentioned, we have been doing actively involved in developing areas, especially in the area of thermal barrier coating, where we have developed few coatings for GTRE, as you mentioned, for turbine coatings using yttria stabilized or pristonium or samarium or even gadolinium. We have got around to the tune of around 75 lakhs or to 1 crore of funding for doing that. And we are able to develop few technologies for coating. And I think when I heard about that, I thought, okay, we are also on par with some of the good institutes we are working on TBC. Thank you very much, sir. At the outset, I would like to thank you for giving such a wonderful talk and covering all the areas. Hope to meet you for further research development along with you. You can also, people can also take his help because I have also taken his help in doing research. He's a wonderful man who gives suggestion wholeheartedly. You can use his knowledge for doing your research. Thanks once again, sir, for giving such a wonderful talk.
Thank you, Dr. Raju. Thank you once again for inviting me, and I thank all the people in the audience who patiently listened to me for 1.5 hours. Yeah. Thank you so much.
Okay. We will close the session, sir, with your kind
Yeah.
permission. Professor Veregoda,
Thank you,
over to
sir. Yeah, all the participants, the next session will be starting at 2:30. Please, all of you join at exactly 2:30 for the next session. Thank you.
Hello, Professor. Professor Berekoda, did Professor join? Professor Devraj, are you able to hear me? Professor Devraj, are you able to hear me? Professor, ಕೇಳಿಸ್ತಾ ಇದೆಯಾ? Professor?
Good afternoon, everyone. There is a small technical issue at the speaker's end. We'll be starting off the session in a few minutes. Thank you.
ಆಯ್ತಲ್ವ ರೀ
Professor Manjunath. Hello, Professor Manjunath.
Sir, tell me, sir.
Can you just rejoin by yourself? You log out, ask all the participants to stay online,
Yes, sir.
and you log out and log in again and see.
1 second, sir. 1 second.
All the participants, just bear with us for a few minutes. There is some technical issue on the other hand. We'll just log out and rejoin. Please be on the line. Manjunatha, log out abadi.
ಬಂತೀವಿ ಮಾತಾಡಿ.
ದೇವರಾಜ್ ಸರ್.
ಅನ್ಮ್ಯೂಟ್ ಆಗಿಲ್ಲಪ್ಪ ಅವ್ರಿನ್ನ. ಅವ್ರನ್ನೇ ಹೋಸ್ಟ್ ಮಾಡ್ರಿ, ಒಲ್ಲಿ ಅವ್ರನ್ನೇ ಹೋಸ್ಟ್ ಮಾಡಕ್ಕಾಗುತ್ತಾ ನೋಡ್ರಿ.
ಹೋಸ್ಟ್ ಮಾಡಿದೀವಿ ಸರ್.
ಕೋ ಹೋಸ್ಟ್ ಮಾಡಿ ಅವ್ರನ್ನೇ.
ಸರ್ ಆಗಿದೆ ಸರ್ ಅವರು. ಸರ್ ಕೋ ಹೋಸ್ಟ್ ಆಗಿದ್ದಾರೆ ಸರ್ ಅವರು.
ಏನ್ ಅನ್ಮ್ಯೂಟ್ ಆಗ್ತಿಲ್ವಲ್ಲ ಅವ್ರದ್ದು. ಅವಲ್ಲಿ ಬೇರೆ ಲ್ಯಾಪ್ಟಾಪ್ ಅಲ್ಲ ಏನಾರ ಡೆಸ್ಕ್ಟಾಪ್ ಅಲ್ಲಿ ಮಾಡಕ್ ಹೇಳಿ ಅವ್ರಿಗೆ. ಫೋನಲ್ಲಿ ಇದ್ದಾರಾ? ಮೀಟಿಂಗ್ ಅಷ್ಟೇ ಮಾಡಿದ್ದೀರಾ?
ಹಲೋ,
ಹೇಳಪ್ಪ. ಅವ್ರಿಗೆ ಓಲಿ ಮೊಬೈಲಿಂದ ಮಾತಾಡಕ್ ಹೇಳಿ. ಅವ್ರಿಗೆ ಮೇಲಲ್ಲಿ ಶೇರ್ ಮಾಡ್ಬಿಟ್ಟು. ಹೌದಾ? ಅಲ್ಲ, ಏನ್ ಮಾಡಿ ಅಷ್ಟಲ್ಲ ಅವ್ರಿಗೆ ಮೇಲ್ ಕಳ್ಸಕ್ ಹೇಳಿ. ಮೇಲ್ ಕಳ್ಸ್ಬಿಟ್ಟು PPT ಮಾಡ್ಕೊಂಡು ಅವ್ರು ಬೇಕಾದ್ರೆ ಮೊಬೈಲಲ್ಲಿ ಮಾತಾಡ್ಲಿ.
Hello, good afternoon. Hello. Hello. Mic testing. Hello.
Yeah, you're audible, Tejesh.
Sir, there is no issue from our side.
Dear participants, another 5 minutes, some technical issue we are sorting out.
Hello? Hello? Can you hear me?
Yes, sir, we can hear you.
Sir, now you are audible, sir. You can share the screen. Okay, sir.
Can you see the PPT now?
Yeah, sir, we can see the PPT. Sir, can you press the button?
Can you see PPT
Yeah, sir,
now?
I can see the PPT. Sir, press. Okay, sir.
Now.
Okay, sir.
Is it okay now?
Yes, sir. Yes, sir. Okay, okay.
So good afternoon, everyone. Warm welcome to the afternoon session of day 2.
Hello?
Hello.
Hello?
Sir, shall we start the session?
Yeah.
Yeah. So good afternoon, everyone. Welcome everyone to the afternoon session of day 2. So I would like to give a small introduction about today's speaker, Dr. Devaraj. Dr. Devaraj has completed his B from Malnad College of Engineering. He completed his M.Tech from SJC Mysore. He is awarded with PhD from IIT Madras. Currently, he is working as professor in Reva University in Department of Mechanical Engineering. His area of interest includes vibration analysis of different materials, materials and metallurgy, pre-atomization and deposition of structural alloys, characterization of materials using OM, SEM, TM, mechanical characterization of different materials, composite materials, powder metallurgy, spark plasma, sintering. Dr. Devarajas has published his works in more than 25 reputed international journals and also has presented his work in more than 8 international conferences. Dr. Devarajas has got sponsored project funds from different funding agencies like VGST, Karnataka Council for Technological UG Upgradation, VTU, DST. Funding obtained from the above agencies is more than 2 crores. Dr. Devarajas is currently guiding 7 PhD students. He has also guided 10 M.Tech students. Apart from his regular duties, he has also taken up additional responsibilities like BOS member, BOE member, hostel warden, NCC coordinator, NSS coordinator, and has also worked at different college levels. Dr. Devarajas has given technical talks at different levels and has also been a judge for student project exhibition at different levels. Dr. Devaraj has taught different subjects like mechanical vibration, mechanics of materials, fluid mechanics, material science and metallurgy, turbo machines, computer aided engineering drawing, nanotechnology and applications, composite materials, mechanics of composite materials. So with a small introduction, now I hand over the session to Dr. Devarajas. Sir, over to you.
Okay, thank you very much for your nice introduction. Am I audible?
Yes, sir, you are audible.
Extremely sorry it was delayed because of the technical snag. Extremely sorry for that. It was delayed by half an hour. Anyway, I am very happy and proud to be a part of this program. So next 1.5 hours, I will be talking on spray atomization and development for the metal matrix composites, and also my talk will be focused on different processing methods. Coming to the outline. The outline of my presentation is introduction to composite materials. So my presentation will also be focused on different processing methods like strip casting, solid state consolidation process, spray atomization, and characterization techniques. So coming to the composites. The composites consists of, that already there are 2 phases or 2 constituents. One is matrix phase, another one is the reinforcement phase. We know that matrix phase is very brittle. and the reinforcement phase is hard and matrix phase is very soft material. Reinforcement phase is there, that is very brittle and hard, because the matrix phase is very soft. We cannot use matrix alone. We need to introduce the reinforcement particles or reinforcement phases. When it comes to the applications, composites are the lighter in weight. There is a high strength to weight ratio. Specific modulus or specific strength is very high. The composites can also be used for high temperature applications and high wear resistance material. And some extreme conditions at high temperature, this materials can also be used at elevated temperatures. So when it comes to the classifications, composites can be classified into two categories. One is based on the matrix material. Based on the matrix material, we know that already it is metal matrix composites, ceramics matrix composites, and polymer matrix composites, that is PMC. Why it is metal matrix composite means the matrix material is made up of metals or alloys. In case of CMCs, ceramics matrix composites, ceramics matrix composites made up of CMCs are made up of ceramics matrix composites. In polymer matrix, matrix material is polymer. That's why it is called polymer matrix composites. The next classification is based on the reinforcement material. The reinforcement, as per the reinforcement material, composites can be classified as continuous fibers, discontinuous fibers. If it is a discontinuous fibers, then again aligned fibers, then random orientation fibers. The fibers not only in the form of the reinforcement material, not only in the form of fibers, it can also be in the form of whiskers or the particles. The whiskers aspect ratio is very important. So, because the whiskers we can expect the strength is nearer to theoretical the strength because there are no defects at all. Other type of composites are, it may be in the form of laminate structures also. Other type of composites are honeycombing structures. Then when it comes to the materials, the metal matrix composites, matrix materials are the metals are alloys. What type of metals are alloys can be used? Aluminum alloys can be used. There are different series are there. 2H series, 3H. To 8H, 8 series are there. Aluminum copper alloy, aluminum zinc, aluminum silicon, aluminum magnesium, aluminum lithium. All these materials can be used as matrix material. Even copper alloys can also be used as a matrix material. Copper, titanium alloys can be used as matrix material in case of MMCs. Whereas reinforcement material in the matrix, metal matrix composites, hard material, hard and brittle material we need to use because aluminum is soft. We need to introduce or we need to incorporate the hard materials like the reinforcement. Reinforcement may be in the form of particles or maybe in the form of whiskers. Sometimes discontinuous fibers can also be incorporated or embedded inside the matrix material. So all oxides, Al2O3, TiO2, SiO2, Fe3O2, all these zirconia, all oxides can be used as reinforcement material. Not only oxides, non-oxides, for example, carbides. Carbides are there, silicon carbide. Silicon carbide is one of the important reinforcement material. Can be used as reinforcement material in case of metal matrix composites. Not only carbides or oxides, nitrides can also be used. Aluminum nitride, silicon nitride can be used as reinforcement material in case of metal matrix composites. The second one, when it comes to ceramics matrix composites, both matrix material as well as the reinforcement material can be used as both matrix as well as reinforcement material. All oxides can be used as matrix material or reinforcement materials. Carbides can also be used as matrix as well as reinforcement materials. Nitrates also can be used as nitrates can also be used as matrix as well as the reinforcement materials. In case of polymer matrix composites, polymers are very soft material. Matrix material is polymer. For example, the phenolics is there. It is a matrix material. Epoxy is also another example. Epoxy and because epoxy and phenolics are the polymer materials. That is polymer materials. Another set of the polymers are thermoplastics. The thermoplastics may be thermoplastics are polyethylene, polyurethane, or acrylics can also be used as matrix materials. Even nylon is also best example for thermoplastics. So these are the matrix materials in case of polymer matrix composites. What are the reinforcement material used in PMCs? Reinforcement materials are carbon fibers can be used as a reinforcement material. Not only carbon fibers, glass fibers are there. The glass fiber, different glass fibers are there. E glass fiber, S glass fiber, C glass fibers can be used as the reinforcement material. In addition to that, the aramids are Kevlar. Kevlar is a trade name for aramids. These fibers or these materials, reinforcement material, can be used in the form of fibers, continuous fibers, discontinuous fibers, whiskers, or maybe in the form of particles. That is about the composite materials. Other type of composite is available in the form of honeycombing structure also. It's a kind of porous material. When it hold on 1 minute. So 1 minute, please. Yeah, when it comes to the processing methods, the metal matrix composites are there. Now, metal matrix composites can be produced with the help of stir casting process. That you can see here from the schematic view. Any aluminum alloy can be made, aluminum alloy, copper alloys, or titanium alloy can be used as a matrix material. It can be melted in a crucible, in a furnace. This is the crucible. Alloy is placed inside the furnace along with the crucible and it is melted. Once it is melted, we need to add the reinforcement material. Reinforcement material may be in the form of oxides. Al2O3 is an oxide, Fe2O3 is an oxide, B2O3, SiO2, zirconia. All these are oxides can be used in the form of particles or carbides. SiC is the carbide particle, B4C is the carbide particles. Nitrates also can be used as the particles, that is aluminum nitrate, silicon nitrate, even boron nitrate can also be used. See here, once it is melted, it is one of the important processes as far the metal matrix materials are concerned. So this cannot be used, this process cannot be used for PMCs, polymer matrix composites or ceramics matrix composites. This stir casting can be adapted only for metal matrix composites. Metal matrix composites can be produced easily with the help of stir casting process. Once the alloy is melted, once the alloy is melted, say here, the particles of oxides, carbides, nitrates are placed inside the molten metal, or it should be placed inside the matrix material, and after that, once it is placed inside the particles are placed inside the matrix material, it should be stirred in order to obtain the uniform distribution of the reinforcement material. Here the stirrer is there, no, the rotation of this stirrer, maybe it is 50 to, it varies from 50 to 100 RPM, slowly it should be rotated. And once it is rotated and uniformly, the reinforcement materials are uniformly distributed inside the matrix material. After that, once the stirrer is over, then we need to pour that molten metal along with the particles. We need to pour that into a prepared metallic die, ready-made metallic die. After solidification, you can get a solid part that is called that is called metal matrix composites. So this is one of the important processing technique as per the metal matrix composites are concerned. Here you see that this is the typical micrograph of as-cast alloy. From this you can see the grains and grain boundaries clearly. See here, this is as-cast alloy. This is the OM optical metallurgical microscope. This is the surface topography of the material. It is clear cut. There is a clear cut grains and grain boundaries could be seen. It is an alloy. So we need to add the reinforcement material. So what you can see from this is how the grains are, whether the grains are coarse grains or the fine grains or ultra fine grains. From this micrograph, it is clear that it is coarse grains, because it is approximately it is 125 millimeter, 125 microns. The size of the grain, each grain is 125 microns. Are you listening to me? Am I audible?
Yes, sir, you're audible, sir.
Okay. See here, this is the OM micrograph. In order to get this micrograph, what you need to do is you have to take the samples, you have to polish it with the help of the standard metallography procedure. Then after that, after etching, you need to prepare the chemical etchant. Then you have to dip that polished sample into a etchant. So after etching, definitely you can see the surface topography like this. This is a typical microstructure of as-cast alloy. Here the cooling rate is very high. The right hand side, one more micrograph we have, that is scanning electron micrograph. This is captured from scanning electron microscopy. Here some elemental analysis can be done. See, there are two phases are there here. One is the bright phase, another one is the dark phase. That could be seen on the right hand side. The bright phase is there. No, the bright phase is Al2C or CuAl2 phase, and the dark phase is the matrix phase. The CuAl2 phase is located along the grain boundaries. That could be seen from this, because it is a brittle phase and it is located along the grain boundaries. Only at few locations it is distributed within the grains also. Because if you get the coarse grains like this, the mechanical properties will not be improved, because as per the, we know that as per the equation, that is Alphy's equation, if there is any grain refinement, definitely you are able to achieve significant improvement in yield strength. That's why grain refinement is very important. So in case of as-cast alloy, grain refinement cannot be done, because cooling rate is maybe in the order of 10 power 3. Grain size is measured with the help of line intercept method. Approximately the grain size is 125 microns as per the as-cast alloy is concerned. So next one is this is the dendritic structure of equiaxial grains. Initially what we have seen is that is the equiaxial grains. Here it is not, they are not the equiaxial grains. You can get a microstructure called dendritic structure. The dendrites are obtained. Here you can see that the primary arm, secondary arm and tertiary arms also. See, this one is the primary arm that could be seen in this figure, and one more branch is there, that is called the secondary arm, and again the tertiary arms can also be seen, because here because of the constitutional there is a the difference in cooling rate. There is a difference in cooling rate. Because of the difference in cooling rate, we are getting this kind of the microstructure. Again, if you get this kind of microstructure, mechanical properties will not be improved. Mechanical properties will not be improved. So in order to improve the mechanical properties, definitely you have to go for other type of the processing methods. So the next type of processing method is called hot press sintering. Hot press sintering, this is also one type of processing method to produce the metal matrix composites. Here alloys or matrix material or reinforcement material should not be melted. It should be in the form of powder only. Both matrix material as well as the reinforcement material in the form of powder. The powder should be mixed, for example, oxides, nitrates, or carbides can be mixed with aluminum alloy. There are different series are there. Once it is mixed, because hand mixing may not be possible to mix it uniformly. That being the case, you have to go for ball milling process. You can mill it for 10 minutes, so it will be uniformly mixed. That is, oxides will be uniformly mixed with matrix material. Then after that, you can see that here it is placed inside the die. This is the die. The ceramic, not only ceramic here, not only ceramic. Even I have shown that, sir. Even metallic powder alloy or metallic powder can also be used. On either side of this, the punches are placed, and the punch we have to apply the pressure in both the directions in order to obtain the green strength. Once the green strength is obtained, you have to put it inside the furnace for sintering process. So if the sintering will be taking place, you have to keep it for about 4 to 5 hours. There is a complete diffusion. Diffusion in the sense migration of atoms from one point to another point or one place to another place. So we can get a solid compact. Like this, with the help of hot press sintering, metal matrix composites can also be produced. Here sometimes we are using the binders. Paraffin can be used as a binder. So binder, after heating, it will be evaporated. This type of process is called a conventional sintering. Conventional sintering, we are giving sufficient time for the material to grow or for densification to happen. There will be definitely grain growth. There is no doubt at all. Initially, if you use 1 micron size powder, after compacting, materials may be bigger than that, maybe 2 microns or 4 microns, 5 microns. Again, the purpose will not be served. If you go for conventional sintering, even metal matrix composites can also be produced. Even ceramic material is one of the important technique for the ceramic materials also. Ceramic composite materials can also be produced with the help of hot press sintering. Whereas in case of metal matrix composites, also we can make use of this processing method. So after compacting that, after sintering, definitely you can get a solid compact. If you test it, definitely there will be a grain growth. The properties will not be improved. In order to avoid this one, we can go for the one more process called spark plasma sintering. This is also one of the important processing technique. Both metallic materials as well as the ceramic materials can be compacted. See here, there is a schematic view showing spark plasma sintering. This is also the powder can be compacted here. Any type of powder, that depends on the material. Or metallic materials or alloy, ceramic materials can also be compacted. Here, one advantage of this is simultaneously pressure and temperature can be applied. In both the cases, that is conventional sintering as well as spark plasma sintering, the material should be heated below melting temperature, below solidus line, because here we are not going to melt it. The alloy or the material or ceramics should be in the form of powder. When you say powder, there are different sizes are available: micron size, nano size, even reinforcement material as well as the matrix material. This powder is there, no? The powder can be placed inside the graphite, the ear that could be seen from this figure. The sample is placed, sample means powder. Powder placed inside the graphite die. Particularly here we are using the graphite die. On either side of this punches are placed. Punches are placed. And simultaneously pressure and temperature is applied. See here what are the important process parameters means sintering temperature. Sintering temperature is one thing. Sintering temperature depends upon the material because the melting temperature of zirconium will be different, melting temperature of metals, alloys will be different. In case of sintering process or hot pressing process, the sintering temperature should be less than below melting temperature, below a solid line. That sintering temperature depends upon the material. Sintering pressure, we can apply 30 megapascal, 40 megapascal, 50 megapascals pressure. And holding time, once required temperature is achieved, you have to hold it for about 10 to 15 minutes. The heating rate also very important. In order to achieve 1000, in order to increase the temperature from room temperature to 1000 degrees Celsius, if you set it 100 degrees Celsius per minute, 100 into 10 minutes more than sufficient to increase to reach the temperature, required temperature. So that's why heating rate also very important. Within 10 to 15 minutes, you can get a compact. Here we are not, by using this spark plasma sintering process, we are not giving any sufficient time to go. Only the temperature will be applied with a small duration. That's why whatever the grains we have, we are going to use, the same grains can be retained even after sintering also. See, this is the working principle. How it works means, see, these are the that on the right hand side have the powder particles. The individual powder particles is only the schematic view. The current is allowed to pass through this. On either side of this, the pressure is also applied. When the small gap is maintained, the spark is produced. You can see that in the red mark that is indicated red color. You can see the spark. The spark will be produced. Even after that, once the spark is reduced, then there will be a contact point. Contact points are established. Current is allowed to pass through this. When it is contacted together, it reaches the melting point. It reaches the contact points. It will be melted. And after melting, a small amount of metal will be evaporated and it will be in the form of electrical erosion wounds. That's why here we are not giving any sufficient time to grow. Only below melting temperature it should be heated. It should be heated and pressure also simultaneously applied. That is the reason why there will not be any grain growth at all. We can retain the same particle size before even before after the sintering process. See here some of the example I will give you that how to sinter the powder particle. See from this micrograph, it is clear that the powder particles of different sizes and shape. This magnification is around 200 magnification. You can see that different varieties of powder particles here. The spherical powder particles you have, elongated powders you have, and that is irregular shaped powder particles also are there. A combination of all these things. If you increase the magnification several times, see this, if you focus only on one powder, only a particular powder, see this will be the microstructure. See this is the left-hand side micrograph, that is, this is the same image, captured at 200 magnification, you can see the powder, different sizes. If you increase the magnification from 2200 to 5000 magnification, really you can see what type of microstructure it is. Only in this micrograph, I have focused only on particular powder. And every powder particle exhibits a cellular structure, equiaxial grains. You see along the grain boundaries. See, these are all the grain boundaries. Something is located. That is called the secondary phase. That phase is called A to C or CuA2 phase. CuA2 phase. This is the powder. This type of powder can be used for spark plasma sintering. After spark plasma sintering, you can get a compact like this. This is the sintered compact. See how before sintering it is in the form of powder. After sintering, see it is in the form of compact. The solid compact you can get. So this is the compact produced with the help of spark plasma sintering. So if you want to know, because the powder particle size is very important, no? Whether it is a micron size or nano size. If it is micron, we have to quantify. In terms of microns, you have to quantify how much of powder we have of 100 microns or 200 microns. How much quantity is there of 50 microns? All those things. This can be measured. The powder size can be quantified, measured and quantified with the help of a laser particle analyzer. Thus, that distribution could be seen. This distribution could be seen here. The powder particle ranges from 10 microns to 500 microns. But here, if you see, if you look at this distribution, the majority of the powder particles are in the range of 100 to 200 microns. 100 to 200. Only few powder particles are there of 400 and 500 microns. So this is the powder particle size can be measured with the help of laser particle analyzer, because we need to quantify whether the powder particles of uniform size or any the distribution we have, or there is any variation. We have to quantify. In order to quantify this, in order to quantify the powder particle, it is one of the important tool. With the help of this laser particle analyzer, definitely we can quantify. We can quantify and we can measure the size of the powder. So next one is, see, this is the compact. See that you can see that this one is the compact. So that is the spark plasma sintered compact. We have to see the microstructure. No, we don't know whether it is densified or not, or it is compacted or not, because there the temperature can be varied, or pressure can be varied. If you do not provide a sufficient temperature, there will not be any diffusion at all. There will not be any diffusion. For example, if the compact sintered at lower temperature, temperature may not be seen, may not be sufficient, so that you can see gaps or porosity in between the powder. So after this is the sample I have taken from the compact only. After compacting, this is the microstructure at lower temperature, because we have to provide a sufficient temperature. We have to activation energy should be there. If the temperature is not sufficient, it will not be compacted properly. See that could be seen in this first micrographs. Here also, see the distribution inside the powder particles. Here also there are two phases are there. One is the bright phase, another one is the dark phase. The bright phase is the secondary phase, and the dark phase is the matrix. There are different particles are there. Particle 1, particle 2, particle 3. That even after sintering also it remains in the form of the particles only, not densified, because the temperature and pressure may not be sufficient. By increasing the temperature, for example, temperature is increased from 400 to 450 degrees Celsius. See, the porosity will be decreasing. See, that could be seen. There will be densification, and there is a migration of atoms from one place to another place. That is called diffusion process. The diffusion will be taking place. Diffusion means migration of atoms. So here the migration may be maybe through grain boundaries, or maybe dislocations, or through some other media, or some other, there may be a mass production also. So here, from first micrograph to second micrograph, the porosity, voids are decreasing, because we are giving sufficient temperature to close this porosity. So after increasing the temperature from 450 500 degrees Celsius, see, we have given sufficient temperature. We have provided sufficient temperature, so it will be densified properly, and the density also improved. If you measure the density here, because of the porosity, you cannot get a theoretical density near to the theoretical density. Whereas in this case, if you provide sufficient temperature, or if you compact at higher temperature, definitely you can get a compact, good compact without any gaps or without any porosity. So these are all the images captured at different magnifications of different compacts entered at different temperatures. These are all the SEM images of the compact. This is the compact. Don't confuse with this. This is the sintered compact. From this sintered compact, I have taken a small piece and polished. After polishing, the images have captured for different temperatures. So here in the first micrograph, there is a porosity. It is not compacted properly. It is not densified. Whereas in this micrograph, right hand side micrograph, it is completely closed. It is densified. Nearly 99% of relative density we have achieved. See, the next processing method is composite materials can also be produced with the help of spray atomization process. Spray atomization process means here we can use this spray atomization process for metal matrix composites. Spray atomization cannot be used for PMCs, polymer matrix composites, or ceramics matrix composites. But this can be adopted or it can be used only for metal matrix composites. But whereas hot sintering process is there, hot sintering process can be used both for metal matrix composites as well as the ceramics matrix composites. But here spray atomization can be used only for to produce only metal matrix composites, but it is a rapid solidification process. Grain refinement can be done. Definitely, the grain size will be decreased. So here, this is the schematic view of showing the spray atomization process. There are 3 units are there. This is the melting unit, and this one is the atomizing unit, and here this one is a substrate or the powder or compact can be collected. Deposition unit. This is the deposition unit, and this is the atomization unit, and this one is the melting unit. And this one left hand side, so there will be one more part that is called particles. Particles can be injected into this powder particles, hard particles, in order to produce a metal matrix composites. The halide should be melted in a furnace. After reaching the molten state. The powder particle should be injected into a spray. After once it is solidified, after that definitely you can get a compact. So when it comes to the construction details of the spray atomization process, here there is a melting furnace where bottom pouring melting and it's a bottom pouring furnace and placed on a stand. And this one is the atomizer. Atomizer is connected to a bottom pouring furnace. In order to convert the melt into a fine droplets. And here this one is at the bottom. There is a table. The table can be raised or lowered in order to accommodate the different spray height. This is the spray height, means from the tip of the nozzle to the deposition surface. This is the copper surface, copper substrate. Copper substrate can be raised or lowered. It can also be rotated with the slow RPM, with the medium RPM, like 50 RPM or 100 RPM, something like that. And it can also be water cooled. This is about the construction details. And the working principle is concerned. Say this one. This is the melting furnace. The alloy is placed inside the furnace, and it is controlled with the help of a control rod. And this nozzle is there. Now nozzle is connected to a gas cylinder. Once the alloy is melted, we have to open the stopper rod. This melt is there. No, it is in the form of liquid. Initially, it was in the form of solid. Once the temperature is reached from room temperature to the melting temperature, it is in the form of liquid. It becomes solid. Metal becomes liquid. Then after that, once it is released, it is in the form. It is allowed to pass through a nozzle. The nozzle is also connected to a inert gas cylinder. Maybe nitrogen or maybe argon gas can be used as the inert gas. When it comes to this tip of the nozzle, this is the tip of the nozzle. Melt is in molten metal. Melt is in contact with the contact with the gas, that is inert gas, the stream of molten metal gets converted into a fine spray. Fine spray. After once it is sprayed, here the hard particles like oxides, nitrates, carbides can be injected into this one. Once it is injected, hard particles we are going to inject that into a spray, and it will be uniformly distributed inside the spray, and it is made to consolidate on a when it is consolidated on a substrate. It is a combination of matrix material as well as the reinforced. So you can get like this, you can get a solid compact. So on the right hand side you can see one more schematic diagram. One more schematic showing the number of the particles, different particles, different sizes of the nozzle. When the molten metal comes in contact with the tip of the nozzle, there is a atomizing of the gas also, inert gas also. Inert gas comes in contact with this metal, gets converted into a droplets are there, bigger droplets are there, smaller droplets are there. The size in between these two the droplets we have. See what happens here is the smaller droplets are there during the flight itself. Solid particles, smaller particles are solidified during the flight and arrive at the deposition. Droplets are there, they do not at all. They do not solidify during the flight, and it form of liquid. These two solid particles or liquid particles are in the form of semi-liquid or semi-solid, semi-liquid state. So it's a combination of liquid droplets, solid. When the solid particle is made to impinge on a liquid droplet, again the drop of liquid or liquid droplets disintegrated into a number of individual particles, and the nucleation sites will be more. That's the reason why the grain, because of the nuclear refinement, grain size can be decreased. Can be decreased by using this atomization process, and composites can also be used. Oxide, carbide, silicon carbide, reinforcement material. So with the help of this pre-atomization process also, we can produce the metal matrix composites. See, this is a typical microstructure. After atomization process, the small step sample polished. We taken the small sample and polished with the help of standard metallography procedure. So this is the surface topography of the spray atomization process sample. See here, compared to ASCAS process, as in case of ASCAS process, we have seen that the bigger grains, they have the grain size maybe in the order of 125 microns. Whereas in this case, it is less than 30 microns. The grain size is measured with the help of line intercept method by drawing series number of lines, parallel lines. Grain size is measured with the help of line intercept method. So average grain size is approximately 30 microns. But one disadvantage is here is porosity. See that could be seen. The porosity, there are some gaps, voids are there. We cannot avoid 1 or 2% porosity will always be there. But this porosity can be minimized. Otherwise, the properties will not be improved by optimizing the process parameter. What are the process parameters in spray atomization means? So the different process parameters are there here. In this case, melt temperature is one parameter. Superheated temperature is another parameter. Gas pressure is the parameter. And one more important parameter is spray height also. By optimizing these parameters, definitely the porosity is there. No, porosity can be minimized. You can decrease it to less than 1%, and the grain refinement can be done. Where is 125 microns? Where is the 30 microns? Yes, it is possible, because here there is the cooling rate is very high. In case of the spray atomization process, we are increasing the cooling rate. We are increasing the cooling rate. By increasing the cooling rate may be in the order of 10 degrees Celsius per.
Sorry for the inconvenience. There is a small technical issue. The speaker will be joining shortly. Thank you. Sir, you are.
Sir, am I audible?
Yes, sir, you are.
Can you see PPT now?
Not yet, sir.
So I think. So now, sir.
Sir, your voice is audible, but PPT is not visible.
PPT is not visible. Is it visible, sir, now? No.
No, sir.
So sorry, sir, it is not connecting. Again, it is doing problem. What do you do?
Dear participants, sorry for the inconvenience. There is a technical issue at the speaker end. It will be rectified and he'll be joining in shortly. Thank you. Please bear with us. Dear participants, inconvenience is regretted. There is a technical issue at the speaker's end is unable to connect. So we are winding up the session for today. We are really sorry for the inconvenience. If time permits, we'll be adding up this session of the same speaker in between somewhere. So the feedback link will be shared to you in the WhatsApp group, and as well as it will be shared in the chat box. So we'll be winding up the session for today. Thank you. And we'll be joining tomorrow exactly at 9:30. Thank you.